This video will teach you how to use R, so you can consider it an introduction to the R language. It may be a little dry because we know so little, so there's very little we can do with R, but this video and the one that follows it will ramp you up very, very fast, and then we'll be making graphs of real data, which gets pretty exciting. So if you bear through the dry material, you'll find your expertise accelerating at a faster and faster rate. What we'll cover in this video is the basics of using RStudio, which will be how we access the R language. Then we'll look at the basics of the R language itself, and then we'll take a look at the different types of data structures that R uses and the different types of data that R recognizes. So RStudio is a program just like any other. We looked at how to download it in the previous video, the introduction, and you should have downloaded RStudio by this point. If you don't have it on your computer yet, please pause and download RStudio and R so you can work along with me as we go through these exercises. When you open RStudio, it launches a window that looks like this, and whether you're using Linux, Windows, or Mac, RStudio should look the same on your computer. You'll have a window with 3 panes in the beginning. It does expand to 4 panes later on, and each pane keeps track of a separate source of information. The pane we'll start with is what you see on the left side of your RStudio window. That's called the console pane, and that's where you're going to type in actual R commands. The console pane has a command prompt at the bottom. It looks like a little greater than sign, and this is where you type in R commands. To begin with, you could type in any sort of math you can think of. R knows math, so you could use the R console as a calculator until you learn more things. So if I typed in 1 plus 1 at the command prompt, then I could hit enter, and what RStudio will do is return the answer that R generates based on my command. So the answer to 1 plus 1 is 2. R's smart like that, it knows that. And what the console shows us So far, we've just put numbers inside of objects. But you could do more than that. There's an object inside of R named world phones. The W and the P are capitalized, so notice that. What I'd like you to do is type world phones at your RStudio command line and see what object comes back. R will show you the contents of world phones. What does it look like? Give that a try, and then we'll go on. So when you typed in world phones, you should have seen something that looks like this, basically a matrix of numbers. This is a data set that shows the number of phone connections in the different continents of the world between 1951 and 1961. So you could see how the popularity of the phone spread in different places. But this is not a number. This is a matrix of numbers. And you could save groups of numbers like this into objects by building a data structure, such as a vector, a matrix, or an array. Let's take a look at how you could do that. So in R, a vector is just a one-dimensional collection of numbers, or information. And you create a vector with the C function. You use C, you put in the pieces of information you want to store in the vector, separate each of them by a comma, and then save that to an object. So this code here is go create an object named vec that contains a vector with 6 numbers in it, 1, 2, 3, 10, and 100. I miscounted, I guess it says 5 numbers. The numbers have a single dimension, and you could think of it as a one-dimensional matrix, or a matrix with just a row in it. To create a matrix, you'll use the matrix command, and the matrix command is a little more complicated than C. You need to give matrix a vector of numbers, and then matrix is going to take that vector of numbers and sort them into a two-dimensional table. So here I'm creating a vector of 6 numbers with the C command, and then I'm passing that to matrix as its first argument, and I'm telling matrix how many rows I want in the matrix that results. Here I want a matrix with 2 rows, and I'm going to save that to an object named mat. And then when I look in mat, I see the matrix that was created. And you see that the matrix has 2 dimensions, and that distinguishes it from a vector. So again, the syntax of the matrix command begins with a vector of numbers to go into the matrix. And then you could use the nRow argument to determine how many rows to put in your matrix. For example, this is a matrix with 2 rows, but we could also sort 6 numbers into a matrix with 3 rows by setting nRow equal to 3. Now, there are many other options or arguments you could give the matrix function in R to create matrices in different ways. We're not going to go through all of those, but when we get into working with functions, I'll show you how you could find out the options of matrix. What I do want to talk about, though, is what happens when you do math with groups of numbers. So if we took our vector of 5 numbers and we added 4 to it, R is going to add 4 to each element in that vector. So remember that number was 1, 2, 3, 10, and 100. Well, now vec plus 4 is going to be 5, 6, 7, 14, and 104. R added 4 to every element in there. If you do multiplication, same sort of thing happens. So I call this element-wise operations. And when you start taking vectors and multiplying by vectors or matrices and multiplying with matrices, element-wise operations go continue to happen. For example, if I multiplied vec times a copy of itself, vec, I'm going to get a new vector, and the first element's 1, and then 4, 9, 100, and 10,000. And this is what R is doing to do that multiplication operation. It's just aligning the 2 vectors, and it's doing the operation between each of the elements in the vectors, one at a time. Now, if you're used to linear algebra, this might be surprising, because normally when you multiply a vector by a vector, you either get a single number or a matrix, depending on whether you do inner multiplication or outer multiplication. Well, here R is going to depart from linear algebra. It's going to move into the programming world. It's going to use vectorized operations and do things element-wise. Later on, this will be a real advantage to you, because we'll start storing variables in our vectors, and when we start multiplying one variable times another, we only want Let's apply some of what you've been learning. What I'd like you to do now is make a vector that contains the number 1, the letter R, and the logical value true. So you'll have to think about how to write numbers, how to write character strings like the letter R, and how to write logical values like true. Create that vector, save it to an object, and then look up the class of that object. Now you're definitely going to need to pause the video to do all this. Once you've done it, hit play. This is the code that will create the vector I asked you to make and check its class. So our vector contains a number 1, the letter R, and the logical value true. And each of those pieces of information by themselves has a different data type. They're each a different class. One's numeric, R is character, and true is logical. But when you look at the class of the vector itself, it's a character string. And in fact, if you go back and look at the contents of the vector, you'll see that all those pieces of information have become character strings. So what is R doing? This behavior is very important to understand because it will happen to you and you'll want to know what's going on. If you think of a vector, the way R thinks of a vector, it's just a space in your computer's memory where R puts in information, like the numbers 1, 2, and 3. And along with that space, there's a little flag that R saves, just one flag, that tells R what sort of data is contained in the vector. In this case, 1, 2, and 3 are all numbers, so R saved the class numeric as that flag. If it is all character strings, it'd save the class character. If it's all logicals, it'd save the class logical. And when R looks at that vector, it first looks at the class flag, and then it looks at the contents and displays them according to their class. But if you put multiple types of data in the same vector, R still only has one flag to flag the class of that vector. So R has to make a decision, which class should it use? In this case, it happened to use the character string, the character flag. And so when we went to look at the data, R first looked up the character flag and said, oh, okay, everything in this vector is characters. And then it displayed that data as character strings. When you put multiple types of data together in a vector or a matrix or an array, R is going to have to coerce everything to the same data structure to choose that flag. And this is how R goes about it. If there's a character string anywhere in the values you're saving, R is going to make everything else a character string. So it'll convert numbers to character strings, it'll convert logicals to character strings. But if your information doesn't contain any character strings, then R will look at what it does contain. If it contains numbers, R will convert the logicals to numbers. Using this method, every true becomes a 1 and every false becomes a 0. And then if there are no numbers, just logicals, will stay logicals. But if you have logicals and characters together, the logicals will become characters. So this method of coercing the data preserves the most information possible. You could actually look at your character strings, even if they used to be numbers and logicals, and tell what they were in the past. The numbers will just be numbers surrounded by quotes, and the logicals will be trues and falses surrounded by quotes. And if you know your data was logical and now it's numeric, you could back transform this relationship to know that all the 1s used to be trues and all the 0s used to be falses. So let's test your knowledge of these things. I'll go through these somewhat slowly so you have a chance to guess at each one before I show you the answer and see how many correct answers you can get. So first, if I make the vector that has 5 and the text 2, TWO, what would the class of that vector be? If you said character, you're right, because 2 is a character string and the number 5 will be converted to characters. If I make the vector that has a true and the letter A in it, what class would that be? Well, hopefully you say character, because it'll be a character for the same reason. Anything that contains a character string will become a character. All right, how about the third vector? What class will this be? Did you say character string? This will be a character string as well, because true, even though it looks like a logical value, has quotation marks around it. And anything with quotation marks around it is technically a character string. So R will treat that as a character string, and it'll convert the 1 to characters as well. And if we take a look at RStudio for a second, you can see exactly how this is going to happen. And I think it's important to see what's going to occur when this conversion takes place. We still have the number 5, it's just surrounded by quotes now. And if we look at 1 and true, where true is surrounded by quotes, we get 1 surrounded by quotes and true surrounded by quotes. All right. So let's go back to this last one. What would happen if we actually did math? No vectors are involved here. We're just adding true to 5. Well, this will give us a mathematical answer. And the answer is going to be numeric. It's going to give us the number 6. So Coercion occurs not just when you put things together in a vector. Sometimes it occurs when you try to do operations that only work with a specific data type. So math in general doesn't work with true and falses, but R uses a rule to make it applicable. Since trues get converted to ones through coercion rules and falses get converted to zeros, you could actually do math with logicals, and R will treat every true as a 1 and every false as a 0. So going back to RStudio, if I add true plus true, R converts them to numbers so I can do the math, and we get 2. And if I add true plus false, R converts those numbers, and we get 1 because the false was 0. Which means I could run a mathematical function like sum, which calculates the sum of a vector on a vectors of trues and falses, and it's going to tell me how many trues are in that vector, because each true will show up as a 1 and get added to the sum, and each false will be a 0 and not go to the sum. So sum's a great way to calculate the number of trues in a vector, and if we use mean, which calculates the average, well then it also does something meaningful. The mean of a logical vector is the proportion of values that were true. So when we learn how to do logical test layers, sum and mean will be some useful shortcuts to use. You can also purposefully coerce data into different data types with the as.dot functions. So as.numeric would convert something into a numeric value, and as.character would convert something into a character string. And there's also as.logical and as.factor. R will try to convert the data that you give these functions into the new type, as long as there's a sensible way to do that. For example, if I ran as.numeric on the character string that contains the numeral 1, it's sensible for R to return the number 1, and it'll do that. But if I ran as.character on the character string that contained the word hello, R doesn't know which number hello should refer to, so it won't make the conversion. It'll give you an error. So here's a question. We couldn't put multiple data types into the same vector, but can we put them into the same matrix? No, we face the same problem. A matrix is just like a vector in R's memory. It has a single slot to record the class, so everything will be coerced to a single data type. And that's true with the arrays as well. But what if you actually want different types of data in the same object? A little bit ago, we looked at a data set that had dates, names, and whatnot that came from Excel. Excel can handle multiple types of data, so we should hope that R can too. Otherwise, we might just stick with using Excel. Well, R can. You need to use a different type of data structure to include different types of data. And you can use a list or a data frame. So a list is similar to a vector. It's a one-dimensional grouping of objects, but those objects can be any different type of data that you want. If you look at the class of a list, you'll see that it's a list. So a list no longer has one of the basic class because its elements can contain different things. So the class of list is itself a list. To make a list, use the function list. Use it just like the C function. Put in the different elements of the list separated by a comma. Instead of turning them into a vector, R will turn them into a list. And if you think of a vector as looking like this, a collection of objects with a single flag, a list looks like this, a collection of objects, and each object has their own class flag. So now we can make a list of 1, R, and true. Each will be what it was, its own data type, but they'll still be collected together into a single data structure. Lists are very, very versatile. You can put different types of data in a list, and you can even put different data structures into a list. So you don't have to combine single numbers with each other or single character strings. You could actually put a vector as the first element of a list, or a second element, or another list as an element inside a list. So a list is a recursive data structure. You can combine multiple other lists together in a new list. In fact, you could think of lists as just the all-purpose glue in R. If you want to take any data structures, no matter what they are, and put them together into a single object, you could combine them in a list, and it will work. So this is how I'd write a list, a new list, that contains a vector, a single logical, and then a second vector of character strings. So if we actually create this list in RStudio, let's copy and paste in the command in here. This is how R displays the list. It's sort of a two-dimensional display because it needs to be able to show us that, for example, in the first element of the list, we actually have a vector in there. And then the second element, we have a single number in that element, true. And then the third element, we have another vector here. So this is what a list looks like. The double brackets show you which element of the list you're looking at. And then inside each element, there's whatever object we put there. So a list is the one-dimensional way to include multiple data types together. There's also a two-dimensional way, a sort of tabular structure known as the data frame. So a data frame is R's equivalent to the Excel spreadsheet, if you're familiar with spreadsheets, or tables in other languages. It's basically a table, and each column could be a different data type. So you can have a column of dates, a column of names, a column of numbers, and a column of true and falses, or whatever else have you. To make a data frame, you could use the data.frame function, and what data.frame expects is vectors to use as columns in the data frame. So the first argument should be a vector. That'll be the first column of your data frame. And then the second argument will be the second column, the third argument, the third column, and so on, each a vector. But to be honest, you won't spend most of your time making data frames manually with the function data.frame. Normally you have so much data you don't want to be typing it in. One, that's a pain, but two, you could create typos if you do it. Normally you're just reading in files that already have data frames. However, data.frame is the way to go if you want to make one from scratch. And if you look at the class of a data frame, it'll be called data.frame. So this code's going to save the data frame as an object called df. And take out the space here. And then if we look at df, this is what it looks like at the moment. We have 3 columns. The columns have fairly weird names because we didn't set any names, but we'll learn how to do that pretty soon. And then each of the column has the values of the vector that I gave for that column. 1, 2, 3, RST, true, false, true. So it's not as pretty as an Excel spreadsheet, but these existed before Excel existed, so they're current for their time. If you think of our matrix structure with its single flag, then you could think of a data frame like this. Each column in the data frame gets its own flag. So within a column, you still need to use the same type of data, but between columns, you can use different types of data. That might sound kind of limiting when I put it that way, but it's actually what you want if you're working with data as a data scientist. If you're studying a variable, all the measurements of that variable will be the same type of data. If one of the measurements was a different type of data, then it probably came from a different variable. And then you might study different variables that each have their own type of data and put them together in a structure like a data frame. So this is exactly what you get in Microsoft Excel, in Apple Numbers, and similar programs. OpenOffice has this spreadsheet program. And it's a very versatile, very useful way to store your data. Now remember, I showed you that data frame, and it had really weird names, or some default names that are pulled out of the data we gave it. It'd be better to give sensible names to our data frame, or to any object where we really want to label our values. And you could set names for a vector, a list, or a data frame when you create the vector, list, or data frame. This is how you do it. Here I'm creating a new vector called nvec because it's named, and it still contains the values 1, 2, and 3. Well, it does contain those values, but I want to give each of those values an explicit name. The first value is going to be called 1 spelled out. The second will be called 2, and third called 3. And all I have to do is use those names when I create the vector. So give it the name equals the value for each element in the vector. When you display the vector, what you'll get is the contents with the names floating above the contents. If I create my vector, and then I look at it, the names appear above the contents. The names are just metadata. They're there to help you and other humans read the contents and understand them. If I did math with nvec, add 1 to everything, the names won't get in the way. The values will change. Perhaps they won't align with the names I carefully chose for my values, but the names aren't going to limit me from doing anything I want to do to those values. If you want to give names to a list, you could do that the same way. Just set the name equal to the values of that element. And this time, a list will incorporate the names into its display a little differently. Instead of having the double bracketed 1 for the first element, it'll use a $sign and then the name of the first element, and a $sign and the name for the second element, and so on. And then if you want to give names to a data frame, same method, name equals the contents of that column. And then your names will appear at the top of the column, sort of as a header row, although it's not an actual row of the data frame, it's just the names being shown above the data frame. If you ever find yourself typing a data frame manually, you will almost certainly use names because artist names aren't very sensible. And normally there's so much information in a data frame that you need to explain what it is if that data frame is going to be useful. And your column names are how you do that. All right. Once you have an object that has names, you could explicitly pull out the names to look at them with the names function. So if you run names on an object, it will return a vector of the names as character strings for that object. So for example, the names of that NDF data frame I made on the last slide would look like this: numbers, letters, logic. And this, what names gives me back is a vector. So I could use that as a vector and put into the paste function or whatever function uses vectors. You could also use the names function to change the names of an object. And that syntax is at the bottom of the slide. Call the names vector, the names function on your object, and then assign into it the new set of names that you want to use. So your new set should be a vector of character strings, just like the outputted names would be originally. And the number of names in your new vector should be equal to the number of names in the object. What R will do is it'll replace the original names of the object with your new set of names. So here I could change the names of NVEC from English to Spanish with this code on the screen. Okay, so let's review. We've come a long way. We've learned all the data structures, or the 5 biggest data structures in R, and this is what they look like. We have vectors, matrices, and arrays, which all store a single type of data. And then we have lists and data frames, which can store multiple types of data. Vectors and lists are a one-dimensional way to group data. Matrices and data frames are a two-dimensional grouping, and arrays are an n-dimensional grouping. R doesn't have the equivalent of a list or a data frame for multi-dimensional data of arrays, but you could create a list of lists and so on. You might ask, why would you use a vector, matrix, or an array since they all contain a single type of data? Well, there are places where that is a real advantage. If you know you want to do math with something, that data is all going to be numbers, and if you make a matrix, R can work with it much faster by assuming that they're all numbers than if you create a data frame and try to work with it that way. That said, the pieces of the data structures that I think you will use the most often in R will be vectors, data frames, and lists. Because a data frame is set up to store tabular data, which data scientists work with. And each column in the data frame is a vector, so you'll be frequently extracting columns as vectors and working with them. And then lists are useful because they group multiple pieces of information together. Each of these structures has helper functions that you could use to do things like create them, or change from one data structure to another, or to check that something actually is a vector or a data frame, whatnot, to get the names. And then also you could check the dimensions of each of these structures with functions keyed into that structure that check the dimensions. Now, there are thousands upon thousands of functions in R, and we're not going to cover all of them during these videos. That wouldn't be possible. But I want to sometimes show you functions that might be useful at a secondary level that you could follow up on your own if you like. And this table here is one of those times. So if you think that you might want to look at the dimensions of a data structure, check out the data structure and the function that corresponds to it, and try using that code. In the next video, we'll come back and we'll look at how you can access data that you've stored in one of these data structures. So now you could save a data set in R with a structure, put it in an object, but you don't know how to pull out a value that's buried inside a structure. That's what we'll learn. In this video, we'll look at the syntax of R and how you could use it to take information that you've stored in R out of the data structure, so you could use it with your own functions and you could start analyzing it. We'll begin by looking at the syntax we'll use to subset data. So that's how you extract information from a data structure. You subset the data structure to the piece that you want. Then we'll look at using R packages. I'll tell you a little about what those are when we get there. And we'll look at how to use logical tests and missing values with the R language. So let's start with the question. We could make some vectors here like x, which contains nothing but zeros except for 1, 1. And then we could save that vector x to a vector named y. And when we do that, y will be the same vector. It'll have all zeros and 1, 1. But what if we just wanted to save that special value, that 1, to the element y? That would be a useful thing to do, but we don't yet know how to do that. Or what if that 1 was a mistake and we wanted to go back into x and change it to a 0 so it aligns with all the other values? That would also be useful. What we're going to learn now will show you how you could go about doing those two very simple but general operations. I call this topic subsetting, although you could think of it as selection or extraction or what have you. So to begin this lesson, I would like you to create some simple data structures that you could use to experiment with. First, we'll create a vector. Again, I'm going to call it vec, V-E-C. You could call it whatever you like, but if you use my name, your object will align with the code to come. Vec just has some numbers in it. Then we're going to create a data frame that I'm going to call df, short for data frame. And this data frame contains some information about the beetles. Once you've had a chance to create these objects, I want you to think about the code on the next slide. Here we are. This is what vec looks like conceptually, and it's what the data frame looks like, df, as well. The code at the bottom of this slide extracts different pieces of information from these two objects. I don't want you to run the code yet. I don't want you to run it at all. But I do want you to look at the code and try to guess what each piece here does. I mean, it's going to be easy to just move on to the next piece of lecture, but really take a moment and try to make predictions about what's going to happen. I find when I teach in person that when students have a chance and actually wrestle with this, one, they do pretty good. They build some intuition with R, but two, they learn the subsetting with R much, much faster. And everything that you do with R is going to build upon this topic because you're always going to be selecting data to use in some sort of analyses or some sort of graph. So give it a try to make a prediction. Some of this code is unfamiliar, I understand that. Just give it a go, and when you're ready, hit play. The notation that R uses to subset data begins with the name of the object that contains the data you want to select. Here I'm going to select something from the vector named vec, so I'm going to start by writing the name of the vector, vec. Then immediately after the object, you place some hard brackets that look like this, square brackets. This alerts R that you want to extract some information from the vec vector, or the vec object. The information that R will extract will depend on what you put between those brackets. You need to supply R with some sort of index that tells R what exact pieces of information you wish to retrieve. What you put in that index will depend on how you go about it. So the first thing you need to think about when you create an index is how many dimensions are in your object. A vector only has one dimension, so you really only need one piece of information to extract something from the vector. For example, I could extract the number 10 from a vector just by saying I want perhaps the fifth element in the vector. If you're working with something like a data frame that has two dimensions, you'll need two indexes. You'll have to tell the data frame where the information lies on the first dimension, say it's going to be in the second row, and where it lies in the second dimension. In this case, we could extract base, which is in the third row. Those two indexes together will isolate a single piece of information. So you need to use as many indexes as you have dimensions, and if you have multiple dimensions, just separate your indexes with a comma. That's how R will keep them straight. But what should go in the indexes? You have some options. There are basically 4 different subsetting systems that you can use in R. And we'll go through each of them because they're all pretty simple and they all come in handy in different places. The first is to use raw integers, just numbers, or you could use blank spaces, names if your object has them, and even logical vectors. So let's take a look starting with integers. When you put a positive integer between your brackets, you'll subset your data in the most natural way. Positive integers behave just like IJ notation in linear algebra. So, for example, if I supplied the integer 2 in the first index for my data frame call here, R will extract something from the second row of the data frame. The first index will always be rows. Rows come first in R. The second index will refer to columns. Columns come second. If I put 3 in that index, R will then extract the element that's in the second row and the third column, which is base. So if I type df23, R will extract just the element base from our data frame. What if I put a vector of numbers into one of my indexes? So here, instead of just putting 2 for the second row, I'm putting 2 and 4. R will extract multiple pieces of information. It'll extract something from the second row and something from the fourth row. So if you want to refer to multiple rows, combine your indexes with a vector and then pass it into the brackets. Now, if I put another vector into the columns index, R will give me the objects that come in the intersections of those two indexes, which will be the set of 4 values, 1941 in bass, 1940 in drums. Now this is getting a bit abstract, so let's take a look at how this seems in RStudio. So the first thing I did was create the vec and the df object, just like you did. And if we look at df, we could see the data frame as it appears in R, very similar to how it appeared on the slides. And if I subset df, as we did in the first slide, to get the object in the second row, third column, you'll see that R returns bass. And then I have levels, bass, drums, and guitar. Because bass, because the values in this data frame have been saved as factors. Now this raises a question that you might ask, and that is, when did I create a factor? And the answer is, you didn't really, but when you use data frame to create your data frame, R converts all this information into factors by default. If you pass in character strings, R is going to turn them into factors. I think that's a mistake. I don't think that's very user-friendly. It's definitely not beginner-friendly in R. And if you want to avoid that, you can avoid it by adding the argument strings as factors equals false to data frame. Then R will remake the data frame. And when you look at it, it'll look exactly the same. But now when we extract the information, base is just a character string. So that argument told R, don't convert my strings into factors. Unfortunately, that's not the default at the moment in R, but we could easily work around it. So let's go back to subsetting. We see what base looks like. Now let's see what it looks like when we use multiple values in our indexes. So let's see. This is what we did before. And you can see that what we get is a smaller data frame with those 4 values that we described. So this makes it concrete. This is what happens when we run the commands on the slides. So here's a new command. What do you think this would return? We're asking for the second and fourth rows and the third column. So if you said bass and drums, you're right. Those are the values that match that criteria. Sometimes you want to extract swaths of data in your data frame. And instead of listing each of the individual values in your index, you could use the colon operator to make a shortcut. So 1:4 in R creates a vector, the numbers 1 through 4. So that's 1:4 does the same thing as C, parentheses 1, 2, 3, 4, in parentheses. So that's a shortcut that you could use. And once you have that vector, you could use it to subset. So this command here, df 1:4, 1:2, would be a great way to select everything in the first through fourth rows and the first through second columns. The second interesting thing when it comes to subsetting that you might find useful to use is that you can actually repeat an index more than once when you subset. And when you do this, R will extract that value more than once to put in your subset. Your subset might actually end up being bigger than the original data you started with. That's a little trippy, so let's take a look at how that works. If I subset df and ask for the first row 3 times and the second row 2 times, and then I'm just going to ask for columns 1 through 3, so that's all the columns, this is what R gives me back. I get the first row, which applied to John, 3 times, and I get the second row 2 times. So you could create subsets that repeat values from your original data frame. Now you might ask, why would I ever want to do that? It's actually really useful, and I'll show you some places where you can use that perhaps later on. But just know that it's possible. Also, while we're in our studio, let's take a look at that colon operator so we see what it's doing. A colon returns the start value, the end value, and every integer between those values as a vector. So 1:2 is 1 through 2, 1 through 10. And then if we wanted, we could make a very long vector. And here you can see something that I mentioned earlier in the day. This first number in brackets is only an index that tells us what the first number over here is, what order it falls into in the answer. So 45 here is the 45th element in the answer, and that's all this bracket insinuates, which is why you could mostly ignore the brackets. So there are other integers besides positive integers. You could also subset with 0. If you put 0 into your index, R will return nothing. It will extract nothing from your object. So for example, if I wrote vec bracket 0, I'm going to get this exact line back. It says numeric 0. And that's what a numeric object with nothing in it looks like in R. And if I put 0 into the columns and index of a data frame, this is what I'll get back. It'll say, well, here's a data frame. It has 0 columns and 2 rows. R has to spell that out for me because there's no way to really represent that. So you could index with 0 to create an empty object. To be honest, I have never found this useful. The only time I use it is when I'm writing my own code to distribute, and I want to test it to make sure it doesn't break if someone passes an empty object. But you should know that this is what zeros do. Especially if you tend to index starting with 0, you might be surprised if you use that behavior in R. And then finally, you can use negative indexes. And what a negative integer would do in your index is return everything but the index you asked for. So it's the opposite of a positive integer. For example, if I use this to subset vec, it'd give me the 5th and 6th integers of vec. But if I put a negative sign before 5 and 6, I would get everything but the 5th and 6th elements of vec. So I get 6, 1, 3, and 6. The same applies for data frames. If I put a negative index in front of my rows, I would get every row but the ones listed. And if I put a negative index in front of the columns, I get every column but the ones listed. So negative signs really change things, but they could be a very convenient way to extract information when you want to pull out more information than you want to leave behind. At some point, it becomes easier to just describe what you want to leave behind. So, what I'd like you to do is apply what you've just learned to these subsetting commands. They each attempt to subset vec, but they each go wrong. See if you can spot what's happening that's making them go wrong, and then try to fix it. You'll want to actually run these commands on your computer so you can read the error message, which will help you figure out what went wrong. And then you want to run your answer to make sure that it actually works. When you're ready to continue, hit play. Until then, hit pause. So the first prompt of the exercises asks us to look at the expression vec 1 through 4. And when you run it, you'll get an error that says it could not find the function of vec. So what you'll notice is we're using parentheses in this command. And normally in R, parentheses denote a function. You put parentheses at the end of a function to run the function. So when we put parentheses at the end of vec, R thinks we're trying to run a function named vec. But there is no function defined named vec, and hence we get this error message. It's pretty easy to make the mistake of using parentheses instead of hard brackets when you're trying to subset. If we switch the parentheses out with hard brackets, our subsetting expression works as we planned, and we get the first 4 elements of vec. The next expression goes wrong in a way that's a bit more subtle. The expression is this: vec, hard brackets, -1 through 4. And when we run it, we get this message that says, only zeros may be mixed with negative subscripts. To understand what's going wrong here, you might want to actually run our index by itself, -1 through 4. And what you see is it creates a vector of numbers that begin with -1 and go through 4. And this vector contains both positive indexes and negative indexes. So if we try to parse this the way R would, our expression is saying, take the object vec, give me everything but the first element, and also give me nothing, because that's what 0 asks for, and also give me the first 4 elements. Well, this is mixed messages to say the least, and it's no surprise that R gives us an error message. When you subset with integers, you either need to use strictly negative integers or strictly positive integers. It doesn't make sense to use both. Why would this come up in practice? Well, it's very easy to write something like this when you mean to write -1 through -4. If you want to use the negative notation on multiple numbers, you need to distribute the negative sign, which you could do by surrounding the numbers with parentheses, or putting the numbers in a vector and then making the whole vector negative. Each of these will return what we're looking for. The final expression is this, vec 3, 4, 5, and the error we get says incorrect number of dimensions. And this is basically results from supplying 3 separate indexes to an object that only has 1 dimension. The person who wrote this probably meant to say, give me elements 3, 4, and 5, and they just forgot to group those together in a vector to pass to the first index. By grouping the elements together in a vector, you're creating a single index that has multiple elements, and R knows what to do with the single index when your object only has 1 dimension. Look out for those mistakes, and you should do pretty well with subsetting. Here's 2 other commands that use something other than a vector, and they also go wrong. The mat command here refers to the object name matrix that we made in the first module. You might not have loaded that code, so if you don't have mat at your disposal, try to imagine what this code will do. But you could certainly run df brackets 1. What do you think this will return? And then test it out and see if it returns what you expect. This is what our mat object looks like from before. It's the simple matrix that had 2 rows in it. And if we subset this with a single index, then we're going to be treating mat as if it's an object with a single dimension. But we know that Matt is a matrix, which means it has 2 dimensions. So when we do this, we get a number, the number 2, which is actually this element of the matrix right here, the element in the first column, second row. So does this surprise you that we ran this code and it worked? We only provide 1 index, but our object had 2 dimensions. Well, I think it should surprise you. I think it's a bit disconcerting. Normally when you do something that shouldn't work, you hope to get an error message so you could fix your error. In this case, it gave us a number. And there's a reason R did this. And the reason that R did this depends on how R builds a matrix in its memory. So if you want to know how R creates matrices, consider first how R saves a vector. It's just a group of numbers saved together. And if you took your vector and you divided it up into subgroups, and you call those subgroups columns, then all of a sudden your vector would look a lot like a matrix. And in fact, this is a matrix in R. R saves matrices as vectors, and it just keeps track of where one column begins and one column ends. And so when we ask for the second element of our matrix, R relies on its internal representation as a vector, and it finds the second element of that vector and gives us that back. In our case, that second element was the 2, and that's why that 2 appeared when we ran this command. Something similar will happen if you subset a data frame with only 1 dimension. For example, here's our df data frame, and here's the command that we were going to try to use, df2. Data frames are similar to matrices in that at a low level, they're saved not as a data frame, but as a list. So a matrix is saved as a vector at a low level, and a data frame saved as a list. If you imagine a list that has 3 elements, and each element is itself a vector, and those vectors are the same length, well then you could arrange those vectors to go together, and what you'd have would look like a data frame. And in fact, that's how R saves a data frame. A data frame is a type of list, and each element in that list is a column. So when we ask for the second element of our data frame, what we're going to get is the second element of that list, which is a vector. And what R will return is that vector of dates. So if we run this in RStudio, we could see how R does that. And there we see our second column there, which is the second element of the list that the data frame is saved at a low level. So I think this means that it's very important to purposefully provide 2 indexes when your R structure has 2 dimensions. And then if you don't do that, be aware of what R is going to do. This may be something that you feel comfortable relying on. It will work consistently, but at least now it shouldn't be a surprise when it happens for you. Let's move on from subsetting with integers and look at how you could subset with blank spaces. Blank spaces are very easy to understand. If you leave a blank space between the brackets, R will do no subsetting. So for example, if you wrote vec with 2 brackets and a blank space in between, R will just return the entire vector. That might not make a lot of sense. Why would you do that? You probably wouldn't do that. But when it comes to objects with multiple dimensions, a blank space can be a real time saver. For example, if you wanted to return just the first row of data frame, you could provide an index for the rows index and then leave the columns index blank. What R will do is it won't subset the columns. It'll give you every column in that row. So you'll get John 1940 and guitar. Alternatively, you could leave the row index blank, and you'll get every row in the column 2 in this code, which will be 1940, 1941, 1943, and 1940. So blanks are pretty simple. We won't spend much time with them. Now let's look at names. If you use names in your data structure, then you can ask for objects in the structure by name. So let's take our vector and give it a set of names. Hypothetically, we'll call each element of vec A, B, C, D, E, and F. And if you want to give your object vec these names, you could use the code on this slide, names vec, and then store into the set of names. Now, if we want to extract various elements of vec, we could just pass a vector of character strings that contain the names of the elements that we want. So this code would return elements A, B, and D. Alternatively, we could ask for a different set of elements, A, C, and F. And R will return the elements whose names we ask for. This happens very frequently when you work with data frames, because data frames almost always have column names. So it's very common to ask for a whole column from a data frame, and you could do that just by typing in the names of that column. If you want 2 columns, type in a vector of 2 names. The last way of subsetting with R is with logicals, trues and falses. And this method might seem complicated at first, but as you'll soon see, it's very, very powerful and one of the best features in R, in my opinion. If you put an index of trues and falses in your subsetting notation, R will match each false and each true with an element in the object. So for example, our vector has 6 elements. So if we give it a vector of 6 trues and falses, R will match the trues and falses up with the elements. Every element matched with the false will be left behind, and every element matched with the true will appear in our subset. So in this case, our subset will contain 1, 6, and 10. You could do the same thing with the data frame. Here, I'm going to use true logical values to index the rows of the data frame, and I'll leave the columns index blank. So R will pair our index up with the rows, and will return just the rows that get paired with the true. So like I said, this may seem strange. Why would you bother typing out all these trues and falses? I certainly wouldn't want to bother typing them out myself, but you'll soon see that you don't have to type out such vectors. You could create them with logical comparisons. But let's not get ahead of ourselves. To summarize our subsetting notation in R, you could use integers, which can be positive, negative, or 0. You could use blank spaces, you could use names, and you could use logical values. You can combine different indexes to subset an object if you use a different index for each dimension. So for example, you could subset one dimension with integers and another dimension with names, but you cannot combine indexes within the same dimension. So we couldn't use both integers and names to subset the rows of data frame. One type of index per dimension. Now before we move on, I'd like you to test yourself to determine how well you understand subsetting. In our Beatles data frame named DF, the first cell of the first row is John. And you can extract that cell in a number of different ways now. And if you really want to test yourself, what I suggest you do is take 2 minutes and try to write down as many ways as you could think of to extract the John cell. If you can come up with 10 or more ways, then I'd say that you are an expert subsetter when it comes to R. If you could come up with more than 4 ways, you're doing very good. So give yourself this quiz, and then after 2 minutes, resume playing the video to see how you did. Each of these commands here will subset DF to return the John cell. You can see that most of these are just iterations on themes and combining the different subsetting methods. And there may even be ways here to subset John that I haven't included in the cell. If you come up with a way that works and I haven't included in the slide, why don't you send me an email and I'll add it to future versions of the course. Now subsetting is going to get a bit trickier. We're going to try to subset a list. So you may remember this list from before. It's the list that has a vector of numbers in the first element, a single true in the second element, and a vector of letters in the third element. If you didn't create this list before, I recommend creating it right now with the code on this slide. We'll save this list as an object named LST, which is short for list. What I'd like you to do is extract the vector C12, which is the first element of the list, and then run the sum function on it. Sum is a function that calculates the sum of a vector. So for example, if you ran sum on C123, it'd return 6 because that's 1 plus 2 plus 3. Give this a try, and I'll warn you in advance that it may not work. Try to see if you can figure out what's going on, and then once you've tried it, press play to resume the video. This is what our list object looks like, the list we're going to try to subset. And if we want to run sum on just the first element, we'll need to extract that first element to pass to the sum function. So based on what we've already learned, you probably tried to subset out the first element with this notation, list bracket 1 bracket. And when you do that, it does return the first element. But if you were to run sum on this object, you get an error. It says invalid type list of argument. So what's going on here? The sum function, like many functions in R, requires a vector as its input. What we make when we write list1, though, is not quite a vector. If you look closely at this output, you'll notice that it has this double bracketed element up here. What we have is a list with only one element, and that element contains the vector 1 through 2. So since this whole thing here is technically a list, sum refused to operate on it and gave us this error message. Let's look at some other ways we could subset this list. Instead of just asking for the first element, we could ask for the first and second element. And when you do that, you'll get something that's more obviously a list. It has 2 elements now. And you could see what's going on here. We have the vector in the first element and a single true in the second element. And when you start subsetting out multiple elements of a list, you could sort of see why R has to return a list when you subset, because there's no way it could combine true with A, B, and C in a sensible manner to give us anything other than a list back from this command. So when you subset a list, R has to give you a list back to fit all the elements you've asked for, and R retains this behavior even if you only ask for the first element. In short, when you pull something out of a list using single brackets, you will always get a list back. Now this is a bit unfortunate because, like we saw with sum, a lot of functions in R don't want a list, they want to use a vector or a single number. And if putting something into a list meant you can never get it back as anything other than a list, that would be a real downside to using lists. Luckily, that's not the case. R comes with the second syntax for subsetting that you could use with lists and data frames, since they're based on lists. That's very helpful. If we took our list, and instead of using a single bracket to subset, we use two brackets to subset, we get output that looks slightly different. Maybe you could see what's changed here. We get just the vector 1, 2. And if we ran sum on this, our sum function would cooperate with us. So if you use double brackets, you'd get this, and if you use single brackets, you would get this. The difference is the double brackets return the element that was in the first element slot as that element exists on its own. The single brackets return a list that contained the first element. In the R community, a helpful metaphor is developed to help people memorize this quirk, to help people understand what's going on. Let's take a look at that metaphor. If X is a list, you could think of X as something similar to a train. So a train has cars, and inside each car is cargo. And a list has elements, and inside each list is data cargo. And if you ask for the first element of X, R will give you back a train that has one car in it. But if you use double brackets, R will actually unload the car and give you the cargo. So this is what I'm talking about. Let's make this visual. Here's our train. It's the list we made. Now it looks like a train. If you just ask for some elements of the list using single brackets, you'll get a smaller train that contains the elements you asked for. You get the cargo in each of those cars, but they're still inside the cars, and what you're delivering is a train that has cargo inside of it. If you actually want to remove that cargo and deliver the cargo by itself, you need to use double brackets. Even if you're only asking for one car at a time, R is not going to take the cargo out of the car when you use single brackets. When you use double brackets, however, R unloads the car and we get back just the cargo, in that case, the vector 1 and 2. The downside of this notation is you can't extract multiple elements from the list at once, but if you're only extracting one element at a time, you can get back the element as it is with double bracket notation. So here's a quiz. What would this return? We're using double bracket notation to extract the first element, and then we're using single bracket notation on the result. So R will parse this from left to right the same way you'd read it, and the first thing it'll do is extract the first element, which as we just saw will return the vector 1 through 2. And then R will subset that with the remaining subset notation, and it'll extract the second element of that vector, which is 2. So if you thought that this code would return the number 2, you were exactly right. There's one last wrinkle to subsetting that's related to what we just saw, and that's the $sign. The $sign is probably the most common way to subset that you will use in R, and I think now you're prepared to understand what it does. So if you create a list with names, we'll give our list names with the code on this slide, then you could ask for the elements of the list by their name. The syntax that you would use is the name of the list, a $sign, and then the name of the element that you wish to return. You don't have to put quotes around the element's name, and you don't leave any spaces on either side of the $sign. What R will return is just the cargo of that element. So in this case, just the vector that's in the first element. So this would be the same as using the double brackets and asking for the name alpha with this list. Since the data frame is at its heart a list, you could use this notation to return columns of the data frame. Because remember, each column of a data frame is an element of a list that the data frame is at a low level in R's memory. So df $birth, for example, will return the birth column of the data frame. And it will not return the column as a data frame or a list, it will return the column as a vector, because that's how the column exists in the list structure that underlies the data frame. And this is what you get, the vector with the dates in it. This idea here of subsetting a data frame with the column names using the $sign is why the $sign is so popular in R. Most of your data sets will be saved as data frames, and many things that you do to the data need to look at every value of a variable at the same time. For example, if you wanted to take the mean of a variable, you'd have to extract the whole column of values and pass that to the mean function. Or if you wanted to sum the variable, you'd extract the whole column and sum it. And this syntax here is going to be the most concise way, the easiest way to extract that data. The name of the data frame, a $sign, and then the name of the column you want to extract. So you've been very patient, and you now know enough to start manipulating real data. You can extract values from the data, and you know the syntax which will let you extract variables from your data sets. So we're going to start working with a real data set, manipulating in the ways that you might do as a data scientist. But before we could access that data set, you'll need to learn how to use R's package system, because the data that we're going to use lives in an R package. So what is an R package? A package is a group of data sets and functions that someone has contributed to the R language. These functions are written in R, and the data sets are saved as R data structures. They're meant to enhance what R does, to make it do more things for you. R is an open source language, so anyone can contribute packages to the R language. And as I speak, there's about 5,000 packages out there waiting for you to use. This code does not come with R when you download R. It'd be a much larger download if it did. And it doesn't open with R when you start R, because if R opened all these packages, the memory space I would have to search through would be so large that anytime you run a piece of code, it'd take much longer than it currently does. So the package system is a way to add on to R without overwhelming your computer or your memory or all the efficient processes that exist in R. Let's take a look at how the process works. I'll describe it visually, and then we'll look at how you can get a real package onto your computer. So if you imagine a computer, such as the one in this picture here, you have some sort of memory in a hard drive somewhere. You might use a laptop or a tower like this, or even a server. And then you have an R session. And an R session is just when you open RStudio, or when you type R into your command prompt in a terminal window, and your computer starts evaluating R code. That's an R session. And then somewhere out there on the internet, there are some packages of R code that you would want to download. Later today, we're going to be using a package called ggplot2. So in my example here, I've labeled this package ggplot2. When you start your R session by starting RStudio, your computer opens up an R session. You can start writing R code and getting answers at this point. But if you want to use a function that comes in the ggplot2 package, your R session won't know it exists, and you won't have access to that function. To get access, you'll need to download the package that you want, in this case ggplot2, from the internet into your computer's memory. And you could do this by running a command at the command line in R called install.packages. So if I wanted to download a package called ggplot2, I would run install.packages ggplot2. And what R will do is it'll go to the same website where you got R, cran.rproject.org, and find the copy of the ggplot2 package that's saved there. And then it'll download that package to your computer. Since R is downloading something from the internet, you'll want to be connected to the internet when you run this command. After you run the command, that package will exist on your hard drive, in your computer's memory, exactly where R expects to find it. But you still won't be able to use any of the functions or data sets in the package because it's in your hard drive, but it's not loaded into your R session. If you actually want to use one of the functions in the package, you'll need to run a second command that loads the package. That command is library, and if you run library ggplot2, this time you don't need quotation marks to run ggplot2. R will look in its hard drive where it stores packages, find the package named ggplot2, and load it into your R session. And then you'll have access to all of the functions and datasets that come in your package. So to acquire a package, it's really a two-step process. First, you run install.packages to download the package to your computer. You only need to do that one time ever, although you might want to do it again to update your package or whatnot. Then, each time you want to use the package, you run library. You do that every time you start a new R session where you want to use the package. R won't load a package until you ask for it. And again, R does this to keep things nice and trim and fast. Now this is the sort of error that will alert you to the fact that you have a package issue going on. qplot is a function that makes quick plots. We're going to learn a lot about it in the next video, and it comes in the ggplot2 package. But if you were to run qplot right now in your R session, you would get this exact error. It'd say, could not find function qplot. Because as far as your R session knows, there is no function called qplot. That function lives in the ggplot2 package, which we haven't loaded yet. If you ever see that error about a function you know exists, consider the package the function comes in and run library, that package name to load the package. For example, if I ran library ggplot2 now, qplot would start to work. R would find the function, and in this case the function would make the graph you see there, because that's what qplot does. So to summarize, download packages with install.packages, and then the name of the package surrounded by quotation marks, and then load the packages with library and the name of the package. You can surround the name in quotation marks in the second step, or you could not. For library, it doesn't matter. What I'd like you to do is to practice this by installing, downloading, and loading these three packages, ggplot2, maps, and R Color Brewer. Each package does something related to making graphics, and we'll use each of them in the next two videos. To install the packages, you can run the code at the bottom of the slide, the install.packages. Once that code's run, whether you ran that today or you ran it in the past because you already have these packages, then you can use library to load each package individually. So pause the video, take a moment to load those packages, and then once you're done, press play, and we'll look at some data sets that come with the ggplot2 package. The first data set we'll look at is named diamonds, and it comes in the ggplot2 package. Diamonds is a dataset that contains information about 54,000 diamonds that were bought and sold on the open market at a diamond exchange. Hadley Wickham, the author of the ggplot2 package, collected this data from the website diamondse.info. And you can visit that website yourself if you want to see the raw data. The dataset comes in a ggplot2 package where it's saved as a very large data frame. It contains information about the 4 C's related to diamonds, like carat, color, clarity, and cut. And it also measures the diamonds in the data set, and you have information about their depth, their table, their weight, their width, their height. But the most important variable in this data set is the price of these diamonds. So what you have is a description of 54,000 diamonds that includes how much they sold for. You could use this data, for example, to build a model for pricing diamonds. Now, diamonds is a huge data set. I just said I had 54,000 rows. As data sets go in data science, it's not that big, but it is big enough to cause trouble. For example, if you wanted to look at the diamonds object, you wouldn't have a pleasant experience. You could type diamonds into your command line to see what the dataset looks like, but I will save you the trouble of doing that and do it here for you. So if we go to RStudio, we load library ggplot2, and then we type in diamonds, R will show us the diamonds dataset. But since the dataset's so big, R eventually stops displaying it. It shows me the first 1,000 rows. What you can see is these rows have filled up my whole console and even gone back, and filled up quite a bit of my memory buffer. In fact, the first row is already outside of the memory buffer. So although I am looking at the raw data, what I've basically accomplished is to create a data deluge here on my personal computer. And there must be a better way to actually look at this data. And there is. And I will show you a couple ways in a moment, but you actually have the tools to look at the data yourself because you know how to subset data. What I would like you to do is subset the diamonds dataset to show just the first 6 rows. If you're feeling up for a challenge, you could try to subset to show just the last 6 rows. Now to do that, you'll need to know how many rows are in the diamonds dataset. And to do that, you'll need to use one of the commands that appeared in the table at the end of the first video. So consider that a challenge, and don't do that unless you want to. Give yourself a chance to look at these first 6 rows by pausing the video, and when you're ready to resume, hit play. You can subset to just the first 6 rows of diamonds with the command diamonds, hard bracket, 1:6, comma, closing hard bracket. What this will do is it'll extract the first 6 rows of diamonds, and it'll keep all the columns there because we're using a blank space to subset the columns. If you wanted to extract just the last 6 rows, you could first use the nrow function, which tells you how many rows a data frame has. In this case, it will tell us that there are 53,940 rows in diamonds. So it's not quite 54,000 diamonds, but it's almost 54,000. If you just wanted the last 6 rows, then you just have to ask for the last 6 rows, which are rows 53,935 through 53,940. So you could do these things with subsetting, and hopefully you did, but there are functions in R that will do them for you. The head function and the tail function by default do just this. They show the first 6 rows of a data frame, and tail shows the last 6 rows. So let's take a look at that in RStudio. If I run head on diamonds, R will show me the first 6 rows. And even though this isn't very much of the diamonds dataset, it's actually much more useful than what I saw before. Here I could see each of the columns, the column name, and I could see a little bit of the raw data in those columns. So you could tell that, for example, carat is a decimal that's measured to 2 digits. And then color and clarity use some sort of coding system. And price appears to be in whole dollars, and so on. And then if you use tail, you'll get the end of the data set, which can alert you to any changes in the information from the start to the finish of the data set. There's also a function in R called view that you could use if you want to see the data in maybe a more user-friendly way. This function is view with a capital V, and remember that R pays attention to capitalization. So if you type in view with a lowercase v, you won't get the results you're looking for. To use view, run view on diamonds or any data frame, and RStudio will open a table, a data browser, in the scripts pane where you can see your data. Now this table looks like something you'd see in a spreadsheet program like Excel or Numbers, but you won't be able to alter the data in that table. You'll only be able to look at the data. That's the view function, and it can be very handy. Although personally, I don't use it in my workflow that often. I'm comfortable looking at the data as it is in the console. The other thing you could do to learn more about this data set is look at the data's help page. So every object in R comes with its own help page. And if you want to access the help page for an R object, like a function or a data frame, you could access the help page by typing in question mark followed by the object name. So if we want to see the help page for diamonds, we type question mark diamonds. When you type in question mark diamonds in RStudio, here's what you'll see. A help page will open in the bottom corner of your window. This is a pane dedicated to various things, and one of them is help. And what it does is it displays the help pages for R objects when you open them. The font's a little hard to see on my computer, but maybe it'll be easier to see on your own computer. What you'll see in the help page is a brief description of the object. Here we have prices for about 50,000 round cut diamonds. And then we also see some details about this data set. This is a place where the author can tell you about the variables of the data set in a way that he can't really do in the data set itself. For example, there's nowhere in the price column to explain that the prices are in United States dollars, but the help page is telling us that right here. In fact, it's telling us that the prices range from $326 to about $18,000. So things like the Hope Diamond, they weren't sold during the time frame we looked at this data. You also see that carat stands for the weight of the diamond, and you could read about the other variables. Of interest, you'll see that the dimensions are measured in millimeters, and that the depth in the table means certain things by dividing some dimensions by others. So help pages are a very useful way to explore objects that come with R. And you can look at every help page using the same question mark R object syntax. Those variables, like table and depth, that are made by other variables are explained right here in this slide. If you're curious, the depth of a diamond is a ratio between the diameter of the diamond and the up and down axis of the diamond, for lack of a better word. And then the table of a diamond is a ratio of the top upper facet of the diamond to the diameter of the diamond as a whole. And this ratio controls to a little bit how sparkly the diamond is, so it's a variable of interest. If you were to plot this data, and I understand that you don't know how yet, plotting data is going to be the subject of the next video, so just bear with me and examine this plot. If you plot the x dimension by the y dimension of the diamonds, you'll notice that a lot of the data seems to follow on this straight line at the bottom of the graph. I think this is the line of y equals x. So what this is saying is that many diamonds in this data set had about an equal breadth and an equal width. But if you examine this plot closely, you may notice that there are some outliers in the data. In fact, some of these outliers might raise your suspicions about the data. One obvious outlier occurs at 0, 0. That's a diamond that was 0 millimeters wide and 0 millimeters deep. which doesn't seem plausible for a real diamond. I know I myself would not spend $18,000 for a diamond of that dimension, nor would I spend $326. Just above that outlier, or that unusual value, is a diamond that had a depth of maybe, had a breadth of maybe 10 millimeters, but a width of 0 millimeters. That also seems implausible. So I think these are data entry errors, the sorts of things that we may want to remove from our data set before we actually model the data. There's also two outliers to the top of the screen, and these are diamonds. One of them that's over 50 millimeters wide, which is a diamond that's getting into the inches range. I mean, that would be a large diamond, but if we look at its X dimension, it's still only 8 millimeters. So this would be a large pencil-shaped diamond, which I think is implausible as well. Also, at the prices, the relatively low prices these diamonds are selling for, I think that must be a data entry error. And in fact, if you look at that diamond and the diamond in the middle of the page, they almost seem like 2 points that would lie on our straight line, but have some sort of decimal error. The decimal is in the wrong place. So we're going to try to fix these weird values by subsetting them out of the data set. Can you do this? You should be able to. You know how to select everything but a particular value, and you can leave those values behind. But you would find that searching through 54,000 diamonds to identify the ones that are the odd diamonds would be a very tiresome process. So what I'm going to teach you is a way to let R do that searching for you, and it's going to rely on logical tests. So a logical test is just the sort of comparison you've been doing since grade school, asking questions like, is 1 less than 3, is 1 greater than 3, or are these numbers 1 through 5, are each of them less than or greater than 3? So if you actually ran these tests in R, they would return something for you. R is pretty intuitive when it comes to logical tests. If I've run the test 1 less than 3 using the familiar less than sign, which you could find on your keyboard, R will reply true because 1 is less than 3. If I change the test as 1 greater than 3, R will reply false. Now here's a question. If I put a vector into my comparison, is 1 through 5 less than 3, what do you think R will return? Remember how when we did math with vectors, R did element-wise math? For example, I added 4 to the vector earlier, and R added 4 to each element in the vector. Well, when I do a comparison with the vector, R will do a separate comparison for each element of the vector. So this code will return a new vector of trues and falses. You'll notice that there are 5 trues and falses. There are 5 elements in my vector. And what we see here is that the first element corresponds to the first true corresponds to the first element of the vector. So what it's asking is 1 less than 3? Yes, it is, so we get true. The second true corresponds to the second element. Is 2 less than 3? Yes, it is. And then the third corresponds to 3, which technically is not less than 3. The fourth element corresponds to 4, and the fifth element corresponds to 5. So R does the comparison in element-wise fashion. The less than sign and the greater than sign aren't the only operators R uses to do logical tests. Matter of fact, R has several different operators, and they're all listed here on this slide. You see the less than sign, the greater than sign, but also the greater than sign immediately followed by an equal sign, the less than sign immediately followed by an equal sign, a double equal sign, and an exclamation mark followed by an equal sign. Before I go through what these do, I'd like you to think about them and make a prediction about what would happen. At the top of the slide, I defined a vector named x, and it just contains the values 1 through 5. So when I run each of the commands in the leftmost column, R will return a vector of 5 trues and falses. But what's a true and what's a false will depend on the actual operator I use to do the comparison. I've started the table off with the first one. X greater than 3 will test whether or not x is in fact greater than 3. What do you suppose the second element will do? The second element will test whether x is greater than or equal to 3. And you can see the difference in the middle column here. 3 is equal to 3, but it's not greater than 3. So the first operator counts that as a false, and the second operator counts the third element as a true, because 3 is equal to 3. X less than 3 tests whether x is less than 3, and then the less than followed by the equal sign tests for less than or equals 2. And then the double equal sign, any idea what that does? That'll test for equality. So if you want to do a logical test for equality, you use 2 equal signs. And here 3 is the only thing that's equal to 3, so that's the only space where a true shows up. The exclamation mark followed by an equal sign is just the opposite. It'll test for inequality. So everything that does not equal 3 gets the true, and 3 gets the false. And then there's one last operator on this table, And it's actually a bit of a trick question. If you test for x equal to 3, R will not return a true or a false. It won't have to. What you've just run in that command is x gets 3. The equal sign, the single equal sign in R, is similar to the arrow sign we make with the less than and the minus sign. It's assigning 3 into the object x. So you don't need to know whether it's equal to 3 because after you run that, it will be equal to 3. You've just overridden x with 3. It's a very common mistake to use the single equal sign instead of the double equal sign. And as you can imagine, it can sometimes be a bit heartbreaking. So be sure to use the double equal sign when you're testing for equality. And I recommend never using the single equal sign unless you're assigning an argument inside of a function. Because if you're outside of a function, you could always just use the arrow assignment operator, which has evolved into the accepted style for R. Here's another operator that didn't appear in that table. It's the %in operator. And we could figure out what it does through basic induction. If we run the first command on that slide, 1 %in this vector, we're basically asking the question, is 1 in this vector? And as long as 1 is somewhere inside the vector on the right of the in operator, R will give us a true. So %in is testing for group membership. We could confirm this by taking 1 out of that vector. So now 1 is not in the vector 2, 3, 4, and R returns a false. So %in tests for group membership. Now here's where things get a bit tricky. What if I put a vector on the left side of %in? So this time I'll test this vector, 1, 2, 3. Is that in the vector on the right? Because R is so big on element-wise operations, you might be tempted to think that R is going to take the vector on the left and pair it up with the elements of the vector on the right. But %in is probably the one place where R does not do that. It doesn't really make sense to have a group membership operator that divides up the group that we're testing for membership in. What %in is going to do is it's going to test each element in the vector on the left, 1, 2, and 3, independently to see if they're somewhere in the group on the right. So it's going to do 3 %in checks. It's going to check, is 1 somewhere in the group C2, 3, 4? Is 2 somewhere in the group C2, 3, 4? Is 3 somewhere in the group C2, 3, 4? So we'll get 3 trues and falses. And what we see is 1 is not in that group, but 2 and 3 are in that group. Those are the basic operators for doing logical comparisons, but you could create more sophisticated tests by combining multiple comparisons together. And you could do that in R with Boolean operators. So Boolean operator is something like and or the negation sign. They're fairly simple. They're not much more complicated than the regular logical operators. So let's take a look at them. If you want to create a test that tests whether something meets 2 conditions, you could use the and operator. For example, this test would ask, is x greater than 2 and is x less than 9? And R will return a single true or false. It will only return a true if both sides of the test are both true. That's what and does. So for example, when you run this command, R will check the first side of the operator, is x greater than 2? In this case, let's pretend that x is. Perhaps x is 5. So that side has a true. And then R runs the next side of the test, is x less than 9? Well, if x is 5, then that would be true too. And R doesn't return anything yet. It's still just crunching numbers in the background. And now it applies the Boolean operator. It says, are both of these true? Is condition 1 true and is condition 2 true? In this case, they are. And so R returns this. This is what we'll see in our window, a single true. In other words, the operator behaves just as you'd expect it to if you thought about it for a few seconds. For the AND operator, both expressions on either side of the operator must return true for the final result to be true. If either one of them is false or if they're both false, the AND operator will return false. If you want to test for OR, this is a situation where one side can be true or the other side could be true or they're both true. Just so long as one of them is true, you want a true to be returned, you could use the pipe character. The pipe character on most keyboards is above the return button or the enter button. So that's one way of testing OR, and it tests that at least one of them is true. But there's a second way of describing OR. This comes from logic, the philosophical field of logic, and that is one true or the second true, but not both? In this case, you only want true if only one is true. And there's an operator in R that does this, and it's XOR. But it's not an operator like the multiplication operator, the addition operator, or the AND operator. You don't put it between conditions. You use it as a function, the XOR function, and you put two conditions inside the function. If both those conditions resolve to true, the function returns false. If only one of them resolves to true, the function returns true. The exclamation mark is also a Boolean operator in R. What it does is it negates the results of whatever expression follows it. So for example, you could put the exclamation mark in front of an expression that would normally return true, and then that expression would return false. If you put in front of a function that normally return false, that expression would return true. So it just flips the result. And then there are two last very useful Boolean operators. If you have multiple tests that you want to condense down to a single true or false, you could use any and you could use all. What any will do is it'll resolve all the tests, and as long as one of them, at least one of them is true, it'll return a true. If none of them are true, it'll return a false. You use any like a function. All does the same thing, but it only returns true if all of them are true. If even one of them is false, all will return false. So you write all like a function, you give it a vector of expressions, logical expressions, and R will evaluate each of those, and it will only return a single true or false, and it will only return true if all the expressions resolve to true. So it's basically asking, are all of these things true? So here's a summary, a table that can help you summarize the logical operators in R. They're fairly simple to pick up, and once you use them once or twice, you'll have them down pat. And then a second table of the Boolean operators, which I think are just as simple to pick up. To help you practice these things, I've made some objects here that I'm just calling W, X, Y, and Z. And you could put these into your own R session by running this code, or you could just keep in mind what they are, because on the next slide I have some exercises I'd like you to practice. If you have these objects already in your computer, you could test yourself by running the exercises. But you don't have to have these objects to write the code that supplies the answers. Here's what I'm talking about. Each of these sentences is an English way of saying a logical comparison. For example, you might say, is W positive? But you can convert that sentence to R code now. You could write the R test that tests whether W is in fact positive. And that's what I'd like you to do. Go through each of these sentences and use R's logical operators and Boolean operators to try to convert the sentence from English into R. As you do this, press the pause button so you have time to work on these things, and then when you're ready to resume, press play. This is the R code that is the equivalent of the English expressions in our last slide. The first line of code asks, is W greater than 0? And that one was probably very straightforward. The next one asks, is X between 10 and 20? You could do a test for a range like this with the AND operator. So on one side we're asking is X above 10, and on the other side we're asking is X below 20. This will only return true if X is somewhere in that range. We didn't use equality signs on either side, so it's going to be an inclusive range. If you did 10 less than and equal to X, and 20 greater than and equal to X, you could have exclusive range. Next, Y double equals February tests whether or not Y is equal to the word February. So even though I've been illustrating these points with numbers, you could test whether any R objects are equal to each other. In this case, Y is a character string, and this line of code will only return true if it is actually the character string F-E-B-R-U-A-R-Y. Capitalization is important here. The final line of code is definitely the most tricky, and it's going to test whether every element of Z is a day of the week. So if we parse this down a bit, assume that Z is a vector of days and other names. The expression Z percent in percent, and then this vector that contains the days of the week, will return a vector of trues and falses. For each element of Z, it'll return true if the element is in fact one of these days of the week. It'll return false if the element is not. If you want to know whether every element of Z is a day of the week, then you have to condense that result, that vector true and falses, to a single true or a single false. And since we want to know every element, we'd use all to do that condensation. Now, as you were working on this code, you may have made one or more mistakes, because there are some very common mistakes that are easy to make with logical operators. And I want to draw your attention to them to help you avoid them in the future. The first mistake is to be too English when you write R. So it's very common in English, it's natural to say, is x less than 10 and greater than 20? But this is not going to work in R because R doesn't behave or think the way you do, or someone who hearing you speak in English would think. R is going to evaluate each side of the AND operator separately. For the left-hand side, that won't be a problem. X is less than 10, there's a true. But when it gets to the right-hand side, less than 20 is not a complete logical expression. So this will result in an error, and that error will carry through to the result. What you need to do is provide a complete logical test on either side, on both sides, of the AND operator and the pipe operator. The next mistake I already mentioned once, but it's worth highlighting twice. If you use the single equal sign to test for equality, you will end up overwriting whatever's on the left-hand side of the data, of the expression. So don't do that, always use the double equal sign. And then the last line of code here illustrates a couple different mistakes. First of all, we're doing something that seems rational and might work. We're testing whether each element of z is equal to Monday or Tuesday or Wednesday or so on. First off, if you find yourself using multiple OR tests in your expression, then you might consider switching to %in, because %in tests for group membership is z somewhere in this group, and that's a more concise way of asking, is z member 1 or member 2 or member 3 or so on. But the second thing this code is doing wrong is it's not providing a complete test between the OR operators. So when R tries to evaluate, for example, the test Tuesday, it's not going to return a true or false, and that's going to cause an error eventually. If you wanted to proceed like this, you'd actually have to write all z double equal Monday or z double equal Tuesday or z double equal Wednesday, and so on, which would be very verbose. Now, here's where logical operations are going to become your best friend. Remember earlier I showed you how you could subset data based on vectors of trues and falses, but I also implied that you wouldn't want to write those vectors yourself? Well, you may have noticed these logical operators return vectors of true and false. When you apply a logical operation to a single number, you'll get a single true or false, but when you apply it to vector numbers, you'll get a vector of trues and falses. And you could feed those vectors straight into your subsetting index to do logical subsetting. Let's take a look at how that's done, because what it creates for you will be a sort of search and destroy program inside your R code. Recall that we saw some suspicious x values in our diamonds data set. These are places where the x dimension was equal to 0 millimeters, which just doesn't seem logically plausible. And if you wanted to remove those values with subsetting, you could, but you just have to figure out where in the data frame they exist. You know, which row do you actually need to remove? Since there's 54,000 rows, it would take quite a long time to find them. But you could ask R to find them for you. What I'm going to do here is create a test that tests whether each value of x is equal to 0. In the first line of code, I'm extracting the x column from diamonds with the diamonds $x syntax. And then I'm creating a logical test with that column, testing whether each of those rows are equal to 0. In most cases, the answer is going to be false, because most of our x values were in fact real numbers, greater than 0. But some places in this vector there should be a true. I'm going to save that vector to an object called x0s, and then I'll use that object to subset. But I don't want things to be too abstract, so let's look at how this works in the concrete. Let's start with the bare minimum. The first thing I'm going to do is extract the x column of diamonds. Now this is going to be a vector, because columns of data frames are vectors, but it's going to be a very long vector. There'll be 54,000 objects here. So we don't even get to see all the Mars stops after a while. But that's what happens when we extract the x column. Now I'm going to test whether each of these values is equal to 0. I will get a vector of 54,000 trues and falses, a false for every element of x that doesn't equal 0, and a true for every element that does equal 0. So when I run this, I see they're mostly falses. I presume that somewhere near there are some trues, but I don't know exactly where they are. And now I want to use this later, so I'm going to save it to its own object, which I will call x0s. So I save that vector of trues and falses to x0s. Now, if I wanted to subset the diamonds data frame, I could do something like this to pull out the first row, and it will give me, just the first row. And if I wanted to use logical expressions to pull out the first row, I could create a vector of logical expressions that starts with true and then has false, 54,000 times. I'm not going to write that out because we don't have time. But I already have a vector of 54,000 trues and falses right here in x0s. So I'll use x0s to subset diamonds. And when I do, I get back just a couple rows. And you'll notice that these are all rows where x equals 0. In many of these rows, y and z also equal 0. So these are diamonds who either don't exist in our physical dimensions, or for some reason, someone didn't collect the dimension data for these diamonds. Now that we found them, and you notice how quick and easy it was to find them in a data set of 54,000 rows, we could decide what we want to do with them. For example, we could return a data frame that has everything but those rows by using the negation sign. This will flip every true to a false and every false to a true. Or we could maybe do something different with this data. But the key here is that this is very powerful. I mean, I just glossed over it, but you were able to sift through your entire data set by just writing one logical test and then using the subsetting notation. It saved you a lot of time searching through your data to find the values of interest. And this is one of the ways R really shines. It can very quickly apply logical tests to whole vectors, to whole data frames, to return just the elements you're interested in. Now, in the last slide, I made a separate vector called x zeros, but that was an unnecessary step. I mean, it's fine to do it, and it really helped me parse the code, but I could have just put my logical test straight into the subsetting here. For example, in this first line, diamonds $sign x greater than 10, let's go find all the diamonds who have an x value greater than 10 millimeters, so a diamond that's bigger than a centimeter. Diamonds that size normally sell for more than $18,000, so I would be suspicious of any diamond like that in this data set, because our prices here cap out around $18,000. That test spits out a vector of trues and falses that immediately gets absorbed by the subsetting command. It uses that vector in true and falses. I don't need to save that in my memory anywhere else. I could skip that step, and that's what this code does. But it's going to return a data frame that has a lot of rows in it, and I might want to save that somewhere so I can access it later. And so in the second line, I'm saving it to big. I could save it to diamonds. In the last line, if I switched my operator there, I could create a data frame that has all the rows where x is less than 10. These are all the sensible rows. And I could save those to diamonds. And from that point forward, diamonds will always have just the rows where x seems to have a sensible value. But if something goes wrong in this expression here, maybe if I didn't test it or if I made a typo, that error or whatever weird thing it returns is going to be saved over diamonds. And I'll basically be losing my diamonds data frame. So only do this if you know it's going to work, because you really don't want to lose your data due to a simple mistake. In this case, if you do overwrite diamonds, for example, we could overwrite to have just one value here. You could get back the original diamonds data frame with the RM expression. So if you got an R object from a package and you overwrite it, you could remove your copy and return the package copy. It's still there on your computer's memory somewhere. Just like you could return objects that exist in the R language itself somewhere. Once again, if you create your own object and overwrite it, you'll have no recourse. You'll be in trouble. So we found the rows that we want to get rid of, rows where x equals 0. And we could certainly throw the entire row out of our data frame. But there was some legitimate information in that row. The other variables like price and carat, those seem to contain real legit values. And this data set probably took some money and some time to collect. And you should never throw out values that seem real, because that's legitimate information that you can use. So instead of throwing out our rows, what we could do is just mark the x values as missing information. And I'm going to show you how to do that with R, how to use missing values. So just to reiterate, removing an entire row because of one missing value is typically overkill, and you're throwing out good data. It'd be much better just to mark the missing value as missing, and then R will know to avoid using that when necessary, and it can continue to use the real values as they become useful. In R, there's a special symbol that stands for missing information, and that symbol is capital N, capital A. You could think of it as meaning not available, because it's information that we don't have for R to use. And R treats the NA symbol in the way that you would want it to. It understands that's missing information, and it uses it accordingly. So think about for a moment how you'd want R to use missing information. Say you pass R two numbers that you want to do some math with, a 5 and some missing information. R is going to return an answer for you. It's not going to return an error, but what would you want that answer to be? So make a guess as to what R is going to return, and then we'll take a look at it. So this is what R is going to do. It's going to give you back another NA, because you could be adding 5 plus 0, in that case your answer would be 5, or you could be adding 5 plus 1, in that case your answer would be 6, or you might be adding 5 plus 1 million. Since that information is missing, R doesn't know. It doesn't have enough information to calculate the real answer, so the real answer itself is missing information. And that's what R gives you back, an NA. If you ran a function like mean on a vector that contained an NA, what do you think R would return? For the same reasons, R is going to return an NA. The mean of 5 and 5 would be 5, but the mean of 5 and 5 million would be something quite different. And R doesn't know which one to return, so it's going to return the NA. Now let's consider doing logical comparisons. If you compared a piece of missing information to a 3, can R tell you whether that missing information is less than 3? No, R cannot, so it will return an NA. The way I like to think of this is, think of missing information as a box that contains something. Something real is inside the box, but you don't know what it is. So when you start asking questions about the box, usually you have to confess that you just don't know. Is this thing I don't know less than 3? I don't know, so the answer is NA. How about is NA equal to 3? Well, for the same reason, you have to admit that you don't know, and R will give you an NA. Now here's the final one. What do you think will happen when you test whether an NA is equal to another NA? Well, R will again tell you NA. That'd be like asking, is this thing in this box equal to this thing in this box? I don't know what either one is, but are they equal? You really don't know. You have double uncertainty in that case, so the NA propagates once again. This is how missing information works in R. It propagates where it should. If you are uncertain about something due to missing information, then the result itself will be uncertain and be stored as missing information. But this behavior, while useful in some places, does create a few problems that you'll want to know how to get around. So for example, you might have a vector of 54,000 diamonds and one NA, and you might want to take the sum or the mean of that vector, and you'd be kind of disappointed to only receive NAs back. You might be perfectly satisfied to throw out the NA and figure out what the sum or the mean of all the rest of the values are. Well, you could do that in R. You might also want to know where in that vector the NA occurs. Since you can't use the logical test NA equals NA, you'll have to have another way to find that value of NA. And you could do that in R too. So I'll show you how to do these two things. The second one is the more easier of the two. If you want to do a logical comparison and find an NA, you could use the function is.NA. So for example, if I make a vector that has an NA in there somewhere, like this, then I could try to test to find that NA by setting the vector itself equal to NA. But that's going to give me NAs all over the place. The way to do this successfully is to run the function is.NA on the entire vector. Is.NA will specifically look through the vector for NAs. Every time there's an element that's not an NA, is.NA will return false. And every time there's an element that is an NA, is.NA will return true. So here I get 3 falses and 1 true. And now I know where that NA is. It's in the last spot. If I want to look for values that are not NAs, I could just put a negation sign in front of is.NA. Remember, negation flips the results of the test. So now this will tell me all the places where I have a real value, and it'll leave behind the place where I have a NA value. That will be false. So is.NA provides a way to do logical comparisons with NAs. If you want to do something like a sum or a mean and not be derailed by an NA, you could use an argument called na.rm. In R, every function that might be derailed by NAs will contain this argument that is optional. You don't have to use it. By default, most functions have na.rm set to false. Na.rm stands for remove NAs. So when it's set to false, that means the function does not remove the NAs. It does the math with the NAs in there, and will probably give you an NA as a result. When you set na.rm equal to true, then what that function will do is it will ignore the NAs and give you the result as if the NAs weren't there. So if I try to sum b here in the slide, I'll of course get an NA because b contains an NA. However, if I sum b and set na.rm equal to true, then the sum will work. It'll sum everything that's non-NA. So na.rm helps you get around the other problem created by NAs. Now that we know how to work with NAs, and we know that we have some missing values that we want to replace with NAs, we could look at how to replace them with an NA. So far we've used our subsetting notation to extract values, but you could use the very same notation to replace values inside of a data object. This would be helpful to see coded live, so I'll code through this code in RStudio. If we start by looking at diamonds $x, one way to look at it would be with the summary function. So this is another function in R, and what it does is it gives some summary statistics for a vector. Diamonds $x is a vector of x values, and summary shows us what the minimum x value is, the maximum, and so on. You'll notice now that the minimum value is 0 because we have some x's equal to 0. Those are the x's we want to get rid of. Why am I showing you this? Because I need a way to show you that we actually got rid of the x's once we do what we're going to do. If I run summary on diamonds $x and the min is something different than a 0, then that means we got rid of those zeros. So what should we run on this? Well, we figured out in the last exercise that we could use the x0s vector that we made to find the places where the rows of diamonds where x equaled 0. If I don't want to subset the whole diamonds data frame but just that column, then I could still use x0s. It's just a vector true and falses. And this time I'm going to subset the vector diamonds $x, and I'm using this as my one-dimension index. What it's going to do is return just the x values that we see in this data frame above. So that's how I get just those zeros. And this is important because it's just those zeros I want to change. And what do I want to change them to? NAs. I was telling you that you could use the same notation that you used to subset to do assignment. If I find 8 zeros like this, I could change them all to NA in one fell swoop by assigning NA to that output. For example, this line of code is going to look up the places where x0 equals true, and then it'll look up the values of those places for all 0, and it'll overwrite those values with what I put on the right-hand side of the assignment arrow. It's going to overwrite each 0 with an NA. So when I run this, that happens. You don't notice anything. The changes are made in the diamonds data set. You don't have to save the changes. R's doing the assignment right there for you. We just need to satisfy ourselves that those values are actually gone. Now this is why I use the summary command up above. When we look at the summary now, the minimum value is no longer 0. So those zeros disappeared. We replaced them with something. And if you look at the end of the summary command, you can see what we replaced them with. NAs. Summary will tell you how many NAs exist in a vector. When we first ran summary, no NAs exist in that vector, so summary didn't include that column. But now there are 8 NAs. If we look at the data frame of places that were saved in that x0s vector, put this up at the top. If we look at this data frame, we can see what happens to those zeros. Now keep in mind, we made x0s before we changed anything, so x0s is set in stone. It's trues and falses. And the fact that we remove those zeros doesn't change x0s. That's already been saved somewhere else. So when I run this, I get the same rows back. And now we can see that x became NA in all those places. Mission accomplished. The important takeaway from this is that you can use the subsetting syntax to actually replace values. You can use the syntax to pull out values, and you can use the syntax to overwrite the values the syntax identifies. We could also plot the data that's missing those values, and it'll look like this. So now we don't see the suspicious values where x and y equals 0. I've also taken out the larger x values too, and we could really focus in on those diamonds that have an equal relationship. And here we see that there's actually some outliers there that might be more interesting to look at. So this is how you can use subsetting the things that you've learned already to clean your data. In the next video, we'll take a look at how you can visualize your data to make graphs like the one you see here. In this video, we'll learn to use R to start visualizing your data. So there's no better way to get to know your data than to actually look at it. And in this module, you'll learn how to make the graphs that R is very well known for. Beautiful plots that show data from a variety of different ways. And we're going to go about learning how to make graphs in R in a systematic manner. We'll be learning how to make graphs one at a time, from scatter plots to bar charts, histograms. And then we'll look at how we might look at big data. And we'll look at how you could save your graphs. But when I say we're going to learn about making graphs in a systematic manner, what I really mean is we're going to learn a system for making graphs. So even though we're only going to spend about maybe 90 minutes looking at how to make graphs, you'll learn how to make any graph that you can imagine from your data, which is pretty heady stuff if you think about it. Now, one of the people who inspires me most when I actually get into data science, especially data visualization, is John Tukey. John Tukey was an academic in the later half of the 20th century who did a lot with the early stages of computer science, but also a lot with statistics and with data science. In fact, it wouldn't be going too far to call John Tukey the father of data science. And John Tukey had a very high opinion of graphs. For example, this quote right here, straight from John Tukey, conveys what he thought. The simple graph has brought more information to the data analyst's mind than any other device. And this is true for a variety of reasons. I think humans are wired as a visual species, but two, the bandwidth that your mind can supply to looking at data in a graph is so much higher than the attention span that you could devote to looking at data in a table. You just can't see things in a table that you'll find in a graph. So let's look at how you make graphs in R. Now, by default, R comes with a function for making graphs known as plot. And it's been in R since the very early days of R, back when R was S. And this is how you'd use plot. You'd write plot, and then the name of a vector of values used on the x-axis, and the name of a vector of values used on the y-axis, and it would make a plot. And this code right here is just using a data set that lives inside of R. It's known as iris, and it makes the plot we see in this slide here. So the iris dataset's kind of well known to statisticians because Sir Ronald Fisher used it for a variety of demonstrations. What it's very good at demonstrating is clustering methods. It's just data about iris flowers. And it turns out there are at least 3 different species of iris flowers, and this data can help you identify those species based on things like the width of a flower's leaf or its petal or the length of the petal, and so on. So this is what graphs look like with plot in R. They're fairly easy to use, low intensity, black and white, unassuming. But we're not going to spend much time using the plot function. There's a couple of reasons for that. Even though plot is R's basic plot method, and even though plot is simple, it does different things in different contexts. So depending on what you give plot, it'll make a different type of graph. And it's not obvious or intuitive what type of graph it makes. You can only pick this up from experience and knowing how to use plot, which means if you're a beginner and new to R, using plot can be a somewhat bewildering experience. And even if you're an old pro at R like I am, I still don't always know what plot's going to give me. And also, plot has been improved upon. I think that the functions that we will be looking at make much more beautiful graphs than plot. And they're also going to be much easier to customize. So there's a real advantage to using a different function, a function I call qplot. And it comes in the ggplot2 package. And ggplot2 stands for the grammar of graphics. It's a package devoting to making graphs in a systematic way. And this is the same graph that the plot would make, but made with the ggplot2 package. And you can see that shows the same data, but the graph looks a little more sophisticated, a little more polished, and a little more like we made it in the past few years, not circa 1983. ggplot2 graphs are very easy to extend. So this is the same data, but now I've just added a color and shape code to help me identify those 3 different species of iris flowers that the data set contains. You notice there's a legend there to help us out. We could also change the actual appearance of the graph if we prefer to have it look like this versus the way it did before. That's easy to do. We could add extra data like model lines. We can completely change the way we visualize the data with density plots or rug plots. And we can even fragment the graph up into different facets to show different things in different places. So all of these features are built into a single system of graphics enabled by the ggplot2 package. And that's what we're going to look at over the next few minutes. So here's some examples of plots that people have made with ggplot2. This plot shows the migration habits of whale sharks off the coast of Africa. So you can see Madagascar down there at the bottom of the graph. And you can see the heavily traveled routes of whale sharks. It's a plot that's made in R from a data set, but it visualizes this data in an interesting way. Here's ggplot2 running displaying some simulation data. These are just different stock portfolios and how they're projected to do over a variety of years. Here's ggplot2 examining a hurricane that struck North Carolina a while ago. We're looking at the wind speeds of the hurricane at different altitudes. Just displaying vanilla sort of data with ggplot2, looking at places where crime occurs in Houston, Texas. You can see the hot zones for crime in Houston, which strangely enough correspond to the city jail in Houston and the Greyhound bus station. And then here's another plot. This is an actual plot, a graph made in R from data that is so beautiful it could appear in a magazine or something. It's a map of London that shows the most heavily traveled bike messenger routes in downtown London. So you can see the Thames River there. If you look closely, you'll notice that you could even see the outlines of buildings and streets and whatnot. And then this grid of yellowy white is the actual streets that bike messengers travel on. And the brighter and thicker a street is, the more heavily traveled it is by bike messengers. So this code was made by a man named James Cheshire. And there's a link at the bottom of the graph that you could follow if you want to learn more about how he made it. He has a whole blog post about it. And on all the previous graphs as well, there's a link at the bottom of the page that you could follow to learn more about how to make that particular graph. But what I'd like to teach you is just the basic fundamentals of ggplot2 to begin with. I would have us build this graph, but unfortunately I just can't get So let's dive right in. Let's build a scatter plot with the ggplot2 package. Now to do this, you'll have to have installed the ggplot2 package, and you'll have to load it with library ggplot2. Now we've done these things in the previous video, but if you shut down R since then, or if you didn't do this in the previous video, you might want to run those 2 lines of code at the top of the slide. There's a data set that comes with ggplot2 called MPG, and it contains data about cars and fuel emissions. And before we look at this data set, and before we make any graphs of the data, we should open the help page for MPG to see what the data shows. So if we go over to RStudio, we could type in $MPG to open the help page, which will appear in our help page pane. And it tells us that the MPG dataset contains fuel economy data from 1999 and 2008 for 38 popular models of cars. We could read right here that it contains information about each of these car models, such as the make and model of the car, the displacement of the engine, which is a measure for engine size, the year of the car, the number of cylinders the car engine has, the type of transmission involved, the type of gas the car takes, and then most importantly, the city mileage that the car gets and the highway mileage. So that's how we'll tell which cars are more fuel efficient than the others. If we wanted to look at the data, we could use the view function that you learned last lesson. And here it is opening up the data in a spreadsheet-like format to take a peek at. But when I talk about looking at the data in this lesson, I mean actually looking at the data, like in a graph. So let's make our first graph of this data set. Before we make this graph, I want you to be invested in it. So please take a moment and make a prediction. What relationship do you think you will find between the fuel efficiency of a car and the size of its engine? In other words, do bigger engines do better or worse when it comes to fuel efficiency? The variables that we'll use to explore this relationship are the displacement variable, which is saved as DISPL in the MPG dataset, which measures the size of the engine, and the highway variable. So we'll look at highway mileage, and that variable is saved as HWY. One way we can explore this data is to graph these 2 variables against each other. And the way we'll do that is with a function called qplot. It stands for quick plot. To use qplot, you first write qplot and start the parentheses behind qplot. And then in those parentheses, you give qplot the name of an x variable. In this case, that'll be the DISPL variable. The name of a y variable. In this case, that'll be HWY. And then an argument named data that's equal to the data set that these variables live in. So you notice I didn't write MPG $displacement. And I didn't put displacement in quotation marks either. Displacement is just the name of the x variable. And normally R wouldn't know where to find that variable because displacement lives in the MPG dataset. But qplot takes this data argument, which allows you to tell qplot where to find displacement. It's going to look in the MPG dataset. And the same will be true for highway. When you run this code, R will make a graph that looks like this. So this is a scatter plot that has highway on the y-axis and displacement on the x-axis. Looking at this graph, you should be able to tell whether your prediction was right or wrong. For example, as displacement increases, you can see that fuel efficiency on the highway decreases. So you call this a negative relationship. And that makes sense. You know, cars with bigger engines take more gas to travel along the highway. So I would describe that relationship as a negative relationship. And to my eye, that relationship looks fairly linear. All these data points pretty much fall in this straight trough that goes, down. But the graph also tells us more than the relationship between the data. Going back to Tukey, the greatest value of a picture is when it forces us to notice what we never expected to see. So you might have spotted something in this graph that you didn't really think about ahead of time, but it's easy to see in the graph. There's some points here that don't fit our trend. I'm talking about these points right here. They're outside of those bars we looked at earlier. So there's something unusual about this group of cars, and this graph has alerted us to it. We'll explore what this group of cars is, and we'll try to figure out why they're unusual, why they're outside of the parameters we saw before. But notice that these are all cars that seem to get better mileage than they should based on the relationship that the other data points display. So what are some cars that you can think of that would get better than expected mileage? Try to form a hypothesis in your head about what those cars might be, and then we'll explore that hypothesis. Here's some variables in the data set that you might use to explore the hypothesis, such as the manufacturer of the cars, the model of the cars, the number of cylinders in their engine, the type of transmission they have, the type of drivetrain. That's like front-wheel drive, rear-wheel drive, four-wheel drive. And then the class of the car. The class variable describes whether the car is like a pickup truck or an SUV or a sedan or a two-seater. And I think that might be the most informative variable here. So what I want to do is incorporate this class variable into the graph I just made, and then use the results to try to determine what cars are disobeying the trend we see the rest of the cars following. Now, to do that, I'm going to have to put a third variable into a two-dimensional graph. And there's only so many ways to put 3 or more variables into a two-dimensional graph. You could add an aesthetic, which means a particular thing, or you could use faceting, which also means something particular. We're going to look at each of these terms of art and see how you could use them to build your graph. We'll start with aesthetics. An aesthetic is a visual property of the marks that appear in your graph. So for example, each of those points in the scatter plot was a round black circle. But we could vary some of their qualities to convey information. For example, we could change the size of the circle depending on the value of, the engine displacement or something. We could change the shape of each circle, or we could change the color of each circle. By changing these visual aesthetics, we can convey a third dimension of information, like our class variable. So an aesthetic is any visual characteristic that can be mapped to data. If you want to use an aesthetic in your qplot, then you could do so by adding an extra argument. The argument should start with the name of the aesthetic that you want to manipulate, such as color, shape, size, and then it should be set equal to a variable in the data set. And what qplot will do is it will map that aesthetic to the values of that variable. In this case, I'm going to map color to class. But you could also map size to class, shape to class, alpha to class. Alpha is a term that refers to transparency. So if you mapped alpha to class, different classes would be transparent to different degrees. When we map color to class, we'll get a graph that looks like this. It's almost identical to our graph before, but now each data point is colored based on the class of the car that data point represents. And not only that, ggplot2 has incorporated a legend into the graph automatically to explain what the colors mean. So if you look at this graph, you might be able to test your hypothesis earlier about what those cars were. For example, we notice that most of those cars are two-seaters, and one of them is a mid-sized car. Now normally when I teach this course live, I ask people what they think is going on here. And before they see this graph, they say something like, oh, those cars must be hybrids because they're getting good fuel efficiency. But if you look closely at the graph, you'll see all those cars have fairly large engines, which hybrids don't. And if you look at this graph, you'll see that most of them are two-seaters, So we're talking about cars with a small body, 2 seats, and a very large engine. And to me, that suggests sports cars. And if you actually looked up these data points, you'd see they're mostly Chevrolet Corvettes, and that green one's a Ford Mustang. So these are cars that have an engine that's as powerful as maybe an SUV or a pickup truck, but the body of a lightweight car. So they get better mileage. There are some hybrids in this data set, but they're the 2 cars way up in the corner that get better than 40 miles per gallon. And those cars have fairly small engines. I think this graph is also interesting because it shows that anything that gets less than 20 miles per gallon on the highway is either an SUV or a pickup, at least in this data set. So that's cool. What I would like you to do is to practice using different aesthetics. Use the color aesthetic, the size aesthetic, the shape aesthetic in your graph. Set these aesthetics equal to different variables in the MPG data set, and pay attention to the variables you're using. Some variables are continuous variables like highway or city mileage. They're numbers that fall on a continuous number line. But other variables are categorical, like class was a categorical variable. You're either in this class or that class, and there's nothing really in between them. Try to pay attention to what happens when you use different aesthetics for categorical and continuous variables, or you could call them discrete and continuous variables, because ggplot2 will behave differently based on whether your variable is discrete or continuous. Pause the video and spend as much time as you want exploring this data, using code like the code in the last slide, and new aesthetics. I think it's fun to make graphs that, on your own. So use this as a chance to get really involved with the ggplot2 package. When you're done, resume the video, and we'll look at how ggplot2 uses aesthetics in different ways for different types of variables. Here's a visual summary of what ggplot2 does with the different aesthetics for the different variables. If you use the color aesthetic for a discrete variable, then ggplot2 will use colors spaced evenly throughout the rainbow to represent the discrete classes. It chooses the colors in such a way that they're very easy to identify to separate from each other, but none of them really leap out as more important than any of the others, which is a good quality to have. If you map color to a continuous variable, then ggplot2 by default uses shades of the color blue. So your colors will start from a really dark blue, almost black, to a really light blue. If you don't like either of those color choices, you can change them, and I'll show you how to do those in the next video. If you map size to discrete, then you'll have different sizes for different classes. And if you map size to a continuous variable, then the size will change continuously based on the values of the variable. If you map shape to a discrete variable, you'll get different shapes for different variables, but if you map it to a continuous variable, you'll get an error message. ggplot2 is not going to let you use shapes to describe a continuous variable. And you could perhaps imagine why. Imagine that you have a triangle on one side and a circle on the other, and you want to continuously morph one into the other. Well, it can be done, and you've probably seen things like that in real life, but I bet you haven't seen that in a graph, because it's very hard for the human eye to tell if half circle, half triangle here is different than half circle, half triangle there. It's just not an effective way to visualize your data. So you're not going to be able to use shape for continuous data. We could describe these things in words as well, but I think since we're talking about a visual medium, the visual summary works best. Let's take one more look at the shape variable, because there's a couple of complex issues going on there that aren't summarized in this table. Some of you may have made a graph that used the shape aesthetic and set it equal to class. Class is a discrete variable, so setting shape equal to class should work. So let's do that. I'm going to run this code, and you'll notice some warning messages show up. We'll look at those in a moment. You'll also notice that your plot appears over here where the help page appeared before. This is a dedicated plots pane that will display all of your plots. If you want to look at a plot in a bigger way, you can zoom it out of this window by clicking the zoom button above the plots pane, and the plot will open in its own window. Now it's a little hard to see due to the aspect ratio of my computer, but there are different shapes being used in this graph. And there's a legend in the corner that shows you which shapes correspond to which class. But you'll notice the last class here, SUV, does not have a shape corresponding to it. And the SUVs in this dataset, in fact, aren't being plotted in the graph. So what's going wrong here? Well, the warning messages that showed up can help us understand. The first thing ggplot2 tells us is that the shape palette can deal with a maximum of 6 discrete values, because more than 6 becomes difficult to discriminate. And then it goes on from there. Basically, our dataset has 7 classes, so when we set class equal to shape, ggplot2 uses 6 different shapes for the first 6 classes, and then it's maxed out, and it has no shapes left for the last class. There are more than 6 shapes that you can use in R, but sort of as a matter of principle, ggplot2 will not use more than 6 shapes. The philosophy here is if you have 7 or more shapes, it's very hard to distinguish between them, and you basically have reduced your data to a visual table. You need to go back and look up the values to decide what they mean. So ggplot2 won't let you do that. I can't change that for you, but I do want you to know what's going on so you know to work around it, and you understand what's happening if you see it occur in your own data. Let's take a moment to set shape equals something continuous, like city. And when you do that, you'll get the error message that says, a continuous variable cannot be mapped to shape. Now you know why that is, because we already talked about it, and this is what you would see. Aesthetics are not the only way to add a third variable to your data set. You could also add additional variables using faceting. Faceting is just the technique of taking your plot and breaking it up into smaller plots that each only show a portion of the data. So for example, each small plot will show a facet of the larger data set. I could explain to you how to do faceting, and eventually I will, but you'll learn it much more quickly and much more effectively by trying it out yourself. Each of these lines of code here will facet your qplot in a different way. Pay attention to what you're adding to the code. In some of them you're adding a function called facet grid, and some of them you're adding a function called facet wrap. Run this code and try to determine what the two different functions do. Also pay attention to the arguments of facet grid and facet wrap. You'll notice they change from line to line. See if you can intuit what the differences do when you look at the plot. Now I'd anticipate that you'd spend about 4 minutes doing this, a minute to each graph. So take the chance to do this, and then when you're ready, hit play again and resume the video. I've taken the code from the previous slide and put it into an R script, which will make it easy for me to work with the code. When you ran the first line of code, you should have seen a graph that looks like this. We have one graph that's been broken up into 4 columns. One column shows all the cars that have 4-cylinder engines. If I pop this out, we might be able to see it a little better. So here's all the cars in our data set with 4-cylinder engines. Here's all the cars with 6-cylinder engines, and here's all the cars with 8-cylinder engines. And believe it or not, there's some cars in this data set that actually had 5 cylinders. I think they were Volkswagens. So this is what faceting does. It splits your graph into separate facets of the data. And what we've done here is effectively add the cylinder variable to our data set. What we have is 4 conditional plots, each plot showing the data conditional on a value of cylinder, the 4-cylinder cars, the 5-cylinder cars, 6-cylinder, and so on. Also notice that the plots have been split up into separate columns. When you ran this next line of code, you should have seen this graph. Here the plots are split up into rows, and we're not using the cylinder variable anymore, we're using the drivetrain variable. So the first row shows all the cars with 4-wheel drive, the second row shows all the cars with front-wheel drive, and the last row shows all the cars with rear-wheel drive. What counts for the difference between this graph and the last one? Well, if you look at your code, you can see it fairly easily. They're both adding facet grid to the end of the graph. This is what facets the graph. And this technique of adding a new function behind qplot is something you'll become very familiar with. It's a common way of manipulating ggplot2 graphs. The way these two things differ is in what we give the arguments of facet grid. They each have something that has a tilde in the center of it, and then a variable name. In the first graph, the variable name follows the tilde. So cyl is the variable in the data set that shows how many cylinders a car has. And this graph faceted the data based on the cylinder variable. In the second graph, we use the drive variable, and it faceted the graph based on the drivetrain variable. When you put your variable after the tilde, the graph will be faceted into columns. When you put it before the tilde, it will be faceted into rows. On the opposite side of the tilde, you'll need to put a dot as a placeholder to prevent the opposite dimension from being faceted. If you put a variable name on both sides of the tilde, as in the third line of code, then R will facet the data in both ways, and you'll get a true grid of facets. So let's look at this graph. You'll notice that it's faceted on columns by cylinders, and it's faceted on rows by drivetrain. So what we have, for example, in this plot here is the conditional plot of all the data conditional on cylinders being 6 and drivetrain being F, which stands for front-wheel drive. In other words, these are all the 6-cylinder cars that have front-wheel drive. And then over here, this plot would be all the 4-cylinder cars that have front-wheel drive, and so on. So here we've added 2 extra variables to our data set. So that's maybe easy to understand, but what does this last expression do? It's using a new function called facet wrap, and the difference between facet wrap and facet grid is somewhat subtle. So we'll run this code, and it makes something that seems similar to the last graph. It appears to be a grid of facets, and this time each facet shows a different class of the data. But notice, even though we have a grid, we've only faceted on one variable, in this case class. So we have 2-seater cars, compact cars, and so on. What facet wrap did is instead of faceting this variable the way facet grid would, perhaps we could see how facet grid would. Instead of making a grid where all the different values of class fill up one dimension, here class is filling up each of the columns, facet wrap made a grid that wrapped the columns around to make something that looks more rectangular, or more square, I should say. If you look at this plot, it's a bit hard to see the relationship between the different groups because each of the plots has been really stretched out to accommodate all the plots in one row. But if you look at the plot we made with facet wrap, which I could see by using the back arrow because it's the last plot I made. So there is a back arrow above the graphs pane. I'll take a peek at this. It's all the same plots that were in the grid, but now instead of compressing them all into one dimension, they're being wrapped around in an intuitive way. Facet grid will naturally wrap them around, and it'll count how many spaces it needs to use and figure out the most square relationship when it does its wrapping. So here it makes a grid with 3 columns and 3 rows, and each of these plots looks roughly square. So that's the difference between facet wrap and facet grid. And basically, I would recommend using facet wrap whenever you have one variable to facet on that has many different values. To summarize what we saw with facets, facet grid creates a 2-dimensional grid. You use the tilde notation to decide which variable to put on rows and which variable to put on columns in your grid. If you don't want to facet on one of those dimensions, you can use a dot as a placeholder in that representation. Facet wrap creates a 1D ribbon that's wrapped into 2 dimensions. You don't need to use dots as placeholders. You just use a tilde followed by the variable you want to wrap on. So now that you've had a chance to work with scatter plots, you might consider making different types of graphs, like box plots or histograms, line plots, pie charts, that sort of thing. And when you talk about different types of graphs, like line graphs, box plots, pie charts, they're all graphs that show data, but they use a different object to display the data, a different geometrical object. We're going to look at this concept, which is referred to as geoms in the ggplot2 package. If you look at these 2 plots, you'll notice some striking similarities. The plots are in fact different, but they each use the same x variable, displacement, and they each use the same y variable, highway. If you look hard, you'll notice that they each display the same data. They just display it in different ways. One uses a scatter plot and one uses a line chart. What's different between the plots is the type of the plot, or what you might call the thing the plot draws, or what you might call the geometric object. In the first plot, the geometric object is a point. In the second plot, the geometric object is a line. By changing the geometric object of your plot, you can move from one type of plot to another type of plot to show the same data. If you want to set the geom of your plot, you could set it in a similar way to how you set the aesthetics. Set the geom argument of qplot equal to, in this case, a character string that describes the geom. So you'll have to know the names of the different geoms that are available to you. The geom that I displayed in the last slide is known as a smooth. It creates a smooth line that fits the data in a smooth way. So for example, if I want to make a scatter plot, I could use this code, which is go use geom equal point. Geom equals point is the default geom. So we weren't using it before, but we were still getting this plot. R was setting geom equal to point in the background by default. We didn't have to worry about it. But we could set it explicitly and we'd get the same sort of plot. To make a new plot, you could set the geom to smooth. And then R will display your plot like this. Instead of drawing points to display the data, it draws a smooth line that fits the data to show where the basic relationship between x and y appears. If you want, you could use multiple geoms in the same plot. Usually it's common to show the raw data and then a summary on top of the data, and you could do that by just passing geom a vector of geom names. So here I'm passing it a vector, which I make with the C function, that has both the name point and smooth. And what will happen is qplot will first draw a point plot, or a scatter plot as we call it, and then it'll draw a smooth plot on top of it. I'd like you to use this new technology to try to make the plot here on the right. This plot features a statistical visualization object named a box plot. So it's a plot that shows box plots. If you run the code at the top of this slide, you'll get the plot on the left. It's basically a scatter plot of this data. But since the x-axis is categorical, the scatter plot doesn't work very well, and a lot of the points fall on top of each other. In statistics or in data visualization, it'd be more common to display this data with box plots. So try to figure out how you can use geom to make a box plot. Give it your best guess and run the code. Pause the video while you do it, and when you're done, press play to resume. So if you decide to set geom equal to box plot, then you are definitely on the right track. That's all you need to do to create this plot. It's going to use geometric objects that are box plots, and your graph will look like this. If box plots are new to you, don't be worried. They're just a way to show the distribution of a group of points. So if you think of those points that I showed in the graph on the left earlier, they're all on top of each other. There are a bunch of cars that are two-seaters, and a lot of them have the same mileage, so those points end up on top of each other. Just to help us visualize this, we can imagine stretching those points out next to each other so we can see where all the pile-ups occurred, and it looks something like this. So this is a group of cars arranged along a y-axis. In this case, it'd be highway, but it could be anything depending on the graph you're making. A box plot is a way of representing where those points fall. So every box plot looks like this. It has a line in the middle, and that line corresponds to the 50th percentile, or the median of the data. It's the place on the y-axis where half the points fall above it and half the points fall below it. On either side of the line, there's a box, and the box will extend down to the 25th percentile. That's the point where a quarter of the data falls below it and 3/4 falls above it. And then the top side of the box will be the 75th percentile, which is just the opposite, the place where a quarter of the data is above that line and 3/4 is below the line. The way you can read a box plot is the span of the y-axis that's contained by the box is where all the common values in this group of points fall. The span that's contained by the lines that extend from the box is where all the typical values fall. And then if there are any points that aren't in the box, they'll just be plotted as they are, and those are what you might suspect are outliers. So there's some equations you can use to decide how far to draw those lines out. They're called whiskers, and which points to use as outliers. And ours just go use those equations in the background to do this. For our purposes, I just want you to know that the box plot shows where the common values are and where the typical values are, as well as the outliers. Sometimes we'll hear this span between the 25th and 75th percentile referred to as the interquartile range. And then anything outside 1.5 times interquartile range from the edges of the box are considered outliers. So we have a successful box plot, but we can make this graph more effective by changing the order of the groups along the x-axis. So if you look at the x-axis right now, you'll notice it goes from two-seater to compact to mid-size to minivan and so on. Those groups are arranged in alphabetical order. Now, if we were speaking French or German, those groups might actually be in different places on the x-axis because two-seater might come after compact in French or German. In other words, the ordering on the x-axis is somewhat arbitrary. If you consider this plot for a moment, you'd probably come to the conclusion that it's trying to display a relationship. And it'd be easier to display that relationship if we reordered the x-axis in a way that supports the relationship. So what am I talking about here? Well, we're trying to show the relationship between class and highway. It seems like there's some sort of relationship. Highway values tend to change based on class, and we could reorder class based on the highway values of each group. For example, we can make this plot here. Now, if you read along the x-axis, it starts with pickup trucks, then SUVs, then minivans and two-seaters, and so on. These groups aren't ordered alphabetically, but when you read them off now, you have a sensible listing of groups that go from the groups with the worst average mileage, pickup trucks, to progressively better mileages until you get to compact cars, which appear to have the best mileage. So we've reordered the x-axis in a way that supports the relationship we're trying to show. I did that with a function called reorder, and you could do that too. The way to use reorder is to put reorder around the x variable or the y variable that you want to reorder. In this case, I want to reorder the x variable, which was class. So I'm putting reorder around class. Class is the first argument in the reorder function. There's a second argument that I'm giving reorder. I'm giving it the argument highway. That's the variable I want reorder to reorder class by. What reorder is going to do is it's going to look at all the points in the different groups of class, and it's going to look at their average highway values for each of those groups. And then it'll reorder the x values based on what the averages are. And this is what we get, the graph you see above. This graph is helpful for looking at the data, but there's still something a little bit odd about it. You might notice that the subcompact group has a lower middle bar than the groups on either side of it. Generally, the middle bars go up, the medians of each group increase, but when you get to subcompact, the median dips back down. There's a reason for that. By default, reorder reorders by mean. But box plots show the median, and medians and means don't always align. And it just happens that subcompact has a lower median than midsize, but apparently a higher mean. It would be better for us, probably, if we reordered by median instead of mean, since our display, our geom, the box plot, displays the median and not the mean. You could do this by adding a third argument to reorder. But I'm not going to tell you what that argument is right away. I want you to look up the help page for reorder and try to correct the graph on your own. So let me be clear about what I want. I want you to look up the help page for the reorder function, read it, try to see if you could figure out how to reorder a variable not by mean, but by median. It might be frustrating to read the help page, so if you get too frustrated, just put the exercise down and restart the video, and we'll go through the help page together. But it's very important that you look at the help page on your own first and give it a try before I lead you through it. So press pause now, and when you're ready to go on, press play. When you looked at the help page for reorder, you may have noticed that it wasn't written to be very informative. It is a help page, it's called a help page, but first and foremost, it's a documentation page, which means it's written for someone who understands R and is documenting the reorder function. This means that sometimes we'll encounter things in help pages that don't really make sense in the beginning. And I have some tips to help you use these help pages and to make it less of a bittersweet experience. First of all, if you don't understand something in a help page, it's probably not important at the moment. So you could just scan over the text in the help page until you see things that start to make sense, and then latch onto those parts. Ignore the things that don't make sense, and certainly don't let those things make you panic. There are tidbits, details about the implementation of functions that you don't need to know to use the function. Those details will show up in the help page, and it's okay if you ignore them. And then finally, try out the examples that appear in a help page. So I'll show you what I'm talking about. This is the help page for reorder. And many help pages in R look similar to the help page for reorder. They don't have to have specific areas, but most help pages have the same divisions. They all start with the general description of the function you're looking up. So here we have a useful overview of reorder, and it says, reorder is a generic function. So right away, if I was new to R, I would say, okay, I know what generic means, I know what function means, but I don't think those mean anything important, and the very fact that they're starting the help page by saying this suggests they probably do mean something important that I don't understand. That's true, and you can just skip right over that. The default method treats its first argument as a categorical variable and reorders its levels based on the values of a second variable, usually numeric. Okay, that makes sense, and I kind of already knew that. The next section of the help page will often be a usage section, which shows how to write the function. It'll list the name of the function and any arguments that the function will recognize. So here I see that reorder will recognize an X argument, a capital X argument, a fun argument, an order argument, and so on. Oftentimes, functions will have arguments that are already set to a value. And if that's the case, you'll see that here. For example, the fun argument is set equal to mean, and the order argument is set equal to is.orderedX. When you see that, that means those arguments are default arguments. They have a default value, and you don't have to supply that argument when you run the function. To use reorder, you're going to have to give it two variables, a variable to reorder and something to reorder it by. And those are the little x and big X arguments there, the first two arguments. But you could leave the rest as it is, and default will just use the arguments you see there. The next section of the help page is arguments. And arguments tells you exactly what reorder expects for each of its arguments. So the first argument named little x, reorder expects an atomic vector, which is just a vector, usually a factor. Okay, we know a little about factors. And the vector is treated as a categorical variable, and so on. You can read about each of those arguments. Scanning down, you'll see that the fun argument takes a function whose first argument is a vector and returns a scalar. A scalar is just a single number, whereas a vector is a group of numbers. And it's going to apply that function to each subset of x, determined by the levels of x. Okay. Next, you might find a value section, which tells you a little bit about what the function returns. So this tells me, what sort of value reorder returns. Then you might see various things like authors, also. But the most helpful section of the help page will normally be at the bottom of the help page. Almost every help page will have a section of examples. This is code that uses the function that's guaranteed to work. Our CRAN, the people who host our packages in R, they won't let you submit a function or a package whose examples don't work. That'd be bad to have code that doesn't work. So you could go to the example section of the help page and run the code and see what happens, which is a great way to learn by, example. So if we look at these examples here, we could try running this stuff, or we could just look at the code that's going on down there. One of the first things you'll see is something called byMedian, which is an object being made with reorder. In that case, reorder has taken 3 arguments, spray, count, and median. That might trigger some bells, and you might right away make the leap to decide, well, you know what? If I put median as the 3rd argument of reorder, it might just do what I want. And that's the sort of intuition that I think really helps you when you're learning a programming language. Just try things out. Don't save your results on top of anything, and you'll be fine. You won't mess anything up. And you can sort of learn your way through R by what I call experimental computer science. So in this case, that's exactly what you need to do. The 3rd argument of reorder, the fun argument, is set to mean by default, which is why reorder reorders by means. But you can override that default by supplying your own 3rd argument. All it needs to be is a function that takes a vector and returns a number. Mean takes a vector and returns the mean. Median is the function that takes a vector and returns the median. So if you want to make your graph ordered by median, you could do so with this code. Qplot reorder, and then set the last argument to median, and there's the graph you'll get. Okay, so we've learned a little about geoms, and you've learned a couple geoms. We got box plots down, points, you've seen smooth lines, but there are multiple geoms out there for you to use. And you need to know the names of them before you could really use them. Where can you learn those names? Well, there's a website devoted to the ggplot2 package. It's fairly lovingly crafted by the authors of ggplot2, and it's very, very useful. It's right here at this web address, docs.ggplot2.org/current. If you go to the web page, this is what you'll see. The ggplot2 webpage lists all the geoms that ggplot2 recognizes, and this starts listing other functions in ggplot2. Each of the geoms has a little icon next to it that will help you see really quickly what that geom creates. For example, here's the box plots. Here's a histogram, and there's various stuff there. If you click on any of these, for example, let's click on geom bar. It makes a bar chart. You'll see what you'd see on the help page for geom bars. So you see like usage and arguments, descriptions, details. It tells you which aesthetics that geom recognizes. So different geoms use different types of aesthetics. You could change the shape of a point, but it wouldn't make sense to change the shape of a bar. That bar needs to be bar shaped for a reason. But bars have different aesthetics that points don't have. The best part about these pages, though, is you see actual graphs in the code that makes them. So if you're trying to make a graph in ggplot2 and you want to do something like maybe make a bar chart that's on its side, you could spot it pretty quickly in this website and then look at the code used to make it. And oftentimes, all you need to do is switch out your data set for the one used in the code, and you can recreate the same graph. This is an excellent resource, and I'll bring us back here more than once because I think that this is like ground zero for making graphs in R. There's so much helpful stuff to be uncovered here. Let's apply our knowledge of graphics to the diamonds dataset, the dataset we were looking at earlier. As we move ahead with the dataset, I'm going to introduce you to the codes that the dataset uses. For example, there's a grading scale used for the color of a diamond, and it's alphabetical. The higher in the alphabet the grading label is, the better the color of that diamond. We generally want our diamonds to be white, and the more dingy or yellow they look, the worse the color grade would be. Next, there's a scale for inclusions in the diamond. So this is for the clarity of the diamond. When you pick up a diamond and look through it, ideally it'll be clear like glass and there'll be no blemishes inside the diamond. But you know, diamonds are minerals that grow in the earth and it's not a perfect process, and sometimes there will be occlusions in the diamond. And the more occlusions there are, the less the clarity score of that diamond will be. Now, the clarity scores for these diamonds are things like IF, VVSI, VVS2. So it's a little unintuitive. This comes straight from the diamond industry. I didn't make these things up, but you could see the rankings of these things in this slide. They go from internally flawless, that's what IF stands for, to internal inclusions. I think that's what II stands for. Then SI is probably something like somewhat inclusion, but to be honest, I don't really know. But we don't need to know to make graphs of the data. This data has categorical variables in it as well as continuous variables, so it provides an excellent opportunity to look at graphs that are well suited to categorical variables, like bar charts. What I'd like you to do is run this code here. Recall that X and Z are variables in the diamond's data set. So I'm not talking about like the X variable of the graph, I'm talking about the specific X variable in the data set. Plot that variable against Z, and then plot X by itself, and then plot cut by itself. We haven't plotted plots that only use one variable yet, so pay attention to what happens. When you plot X and Z of the diamond's data set, you'll get a scatter plot of the X and Z values in the data set. ggplot2 tells us that it ignored some rows that had missing values there, and those are the rows we made in the last video. And that's fine. There's no way ggplot2 could plot a missing value. Where would it put it on the graph? So it's just telling us it had to avoid some rows. And this is what the graph looks like. And it's a good reminder that both the X and the Z variable are continuous values, continuous variables. Let's take that code and remove the Z variable. So now we're just plotting the X variable. Here's what ggplot2 gives us. This is known as a histogram. It's basically a bar chart for continuous variables. Whenever you use just one value, one variable, ggplot2 assumes that you want to look at the distribution of that variable. And if it's a continuous variable, a histogram is the tool you normally use to do that. So the default for one continuous variable is to show a histogram. But let's look at a categorical variable like cut or color. If you use one categorical variable, the default changes to a bar chart. So a bar chart's just the categorical equivalent of a histogram. So we'll spend some time looking at both histograms and bar charts using the diamonds data set. To summarize what I showed you in the RStudio session, two variables by default will create a scatter plot, one continuous variable would create a histogram, and one categorical variable would create a bar chart. When you start working with things like bar charts and histograms, the aesthetics that make sense to use begin to change. And one of the first things you'll notice as you explore the data is that color no longer does what you think it will do. So when you talk about coloring in an object that has mass, like a bar, there's now two different ways to color it. You could color in the outline of the object, and if you set the color aesthetic, that's what will happen. ggplot2 will use that information to color the outline of the bar. But normally when you set the color aesthetic, I think you're picturing the whole bar being a certain color. And you can do that, but you have to use a different aesthetic now. And that aesthetic is called the fill aesthetic. So when you make your bar chart, here I'm making a bar chart. I'm being specific here by saying gm equal to bar, but you know that will be the default if you supply one categorical variable. Then depending on what you set as your aesthetic, here I'm going to set equal to cut, you will get a different outcome. If you set that asterisk to color, you will get this trippy psychedelic thing where just the outline is colored. And if you set that asterisk to fill, you will get a solid fill for each of those bars. So don't let this fool you in the future. If you ever see that psychedelic thing, you probably just need to use the fill aesthetic instead of color. All right, let's look at a more sophisticated bar graph. And this bar graph is going to introduce us to something known as position adjustments. So you notice that we've been learning a lot of vocabulary in this lesson. We learned about aesthetics, faceting, geoms, and now we're learning about position adjustments. This vocabulary exists for a reason. You notice I mentioned the grammar of graphics earlier, which is where the GG in ggplot2 comes from. Vocabulary plus grammar creates a language. And I'm going to tie this vocabulary to the grammar at the end of this lesson, and you'll see that what you've really learned is a sub-language about graphics. Position adjustments are part of that language, so let's take a look at them. Here's a bar chart that uses a couple different variables in the graph. See if you can make this bar chart. I'll give you a hint. The x-axis is the color variable, and each of the bars in that chart are filled with the cut variable. So try to make the plot. I think you'll find it a little difficult to achieve. Give it a shot, and when you're done, press play and we'll resume. When you run this code, you'll get a graph that looks like this. It's different than the graph before, and the difference depends on the position adjustment. So take a look at this graph to see what's happening here. You'll notice that there's probably about 20 different bars in there all together. Each rectangle of a different color in a different place, I'm going to consider a different geom. So for example, if you look at the D value on the x-axis, you'll see that there are 5 rectangles above it. And those rectangles are stacked on top of each other. So you have a red rectangle, which corresponds to diamonds that have a fair cut and a D color. You have a brown rectangle, which corresponds to diamonds that have a good cut and a D color, and so on. In the graph we were trying to make, those bars were positioned next to each other, but in this graph they're positioned on top of each other. If you think about where each bar belongs, you can imagine a graph where each bar is directly on the x-axis, and they're all colliding with each other. ggplot2 tries not to let that happen, although you can ask for your bars to collide and overlap with each other. By default, ggplot2 will prevent it by stacking bars on top of each other, but you could also tell ggplot2 to use another method of preventing collisions. And this is what a position adjustment does. To set a position adjustment, it's just like setting a geom in your graph. You use the argument position now, and you set it equal to one of the adjustments that ggplot2 recognizes. Your graph will use that adjustment to avoid collisions in the final result. By default, the adjustment's set to stack, so you never need to write position equals stack, but you can if you want to. You'll get the graph we just saw. Some of the adjustments that you can use are stack, dodge, identity, and fill. Instead of telling you what they do right off the bat, I want to give you a chance to explore the position adjustment argument. Try out each of these lines of code and see what difference it makes in your graph. You could probably understand what's going on just by running the code and looking at the graph. Press pause while you do this, and when you're done, press play and we'll look at the graphs. Here are the different graphs that occur when you use these different values of position. If you use position equals stack, you'll see what we saw before, the graph where each of the rectangles are stacked on top of each other. And if you use position equals dodge, each of the bars will be next to each other or beside each other. And that's how I made the graph at the start of this section. If you use position equals identity, ggplot2 will not try to avoid collisions at all. It looks like in this step that we got a graph that only shows the ideal bars, but that's not true. There are red bars, brown bars, green bars, and blue bars there as well.